A ceiling of ice stretches to the horizon, silent, blinding, absolute. And beneath that silence, an entire world moves in the dark. There are sounds down there that don't belong to any shoreline. Long metallic sweeps, hollow knocks, mournful groans that travel for miles under pack ice. Heard, recorded, replayed, and still not fully understood. There are places where the sea refuses to seal shut. Open water blooming in the dead of winter, recurring like a memory the ice can't erase. Polynyas that appear, vanish, then return decades later, as if the ocean is breathing through cracks we cannot see. There are lakes trapped under kilometers of ice, hidden reservoirs that fill and drain on schedules no one can predict. Water that moves like a secret architecture, carving tunnels, rerouting rivers, rewriting the map beneath Greenland while the surface looks unchanged. There are shipwrecks so preserved they feel suspended in time. Aircraft swallowed by snow, then carried away by moving ice. Crime scenes that drift, compress, and resurface far from where the story began. And there are signs on the seafloor. Deep gouges cut by ice so massive it hints at catastrophes we barely remember, or barely dare to imagine. These aren't myths. They aren't campfire stories dressed up in science. They're real observations, real measurements, real places, documented by satellites, sonar, radar, and the people who went far enough north to hear the ice speak for itself. So settle in, because under this frozen lid, the Arctic doesn't just hide mysteries, it preserves them. And the deeper we drift beneath the ice, the more the line between the known and the unknowable begins to disappear. Let's begin. Far above the silent seabeds of the Pacific and the Mariana Trench lies a different kind of abyss, one that isn't defined by depth, but by stillness. The Arctic Ocean, for most of the year, lies locked beneath a roof of ice so thick it seems eternal. Yet beneath that frozen ceiling, there exists a hidden world alive with sound, a world that hums, groans, sings, and sighs. Scientists call it the under-ice soundscape. But for those who have heard it firsthand through the ears of hydrophones, microphones dropped into the blackness below the ice, the experience borders on the supernatural. It is a sound world like no other on Earth, alien, echoing, and endlessly mysterious. Just a quick note before we continue. The visuals in this video are subtle by design. These stories took time to uncover and even longer to tell right. So if you'd rather just listen, that's perfectly fine. Let it play in the background or settle in and let your mind drift. Either way, the mystery is waiting. Let's continue. When early Arctic explorers described strange noises that seemed to follow their ships through the ice, few believed them. The accounts were scattered through expedition journals from the late 1800s. Stories of ice that spoke, of groaning ridges that wailed through the night, and of metallic notes that rang out across the frozen sea like distant machinery. For decades, these were dismissed as tricks of the wind. But when scientists finally placed hydrophones under the Arctic pack ice in the mid-20th century, the old sailors' tales suddenly seemed less fanciful, because the ice really does sing. In the darkness below the surface, sound moves differently. Water conducts vibration nearly 5 times faster than air, and under the pressure of the Arctic, the effect is amplified. Every shift in the ice, every breath of a seal, every crack of a ridge becomes part of a vast, echoing chorus. At times, the ocean floor groans with the low rumbles of shifting tectonic plates. At others, distant quakes send tremors that reverberate through the ice sheet like the droning of a colossal organ. Then come the sudden metallic sweeps, long, high-pitched notes that rise and fall as though played on unseen strings. To scientists, these noises are data, vibrations to be measured, catalogued, and analysed. But to those listening alone in the polar night, the effect is deeply unsettling. It feels less like a natural environment and more like a sentient one. Early researchers working with the US Navy during the Cold War were among the first to document these sounds in detail. Hydroacoustic stations were placed throughout the Arctic to monitor Soviet submarine activity. But what they recorded was often stranger than anything military intelligence could explain. The tapes captured strange patterns, moaning choruses that seemed to pulse in rhythm, sudden chirps that echoed like sonar, and tones that swept up and down the spectrum like a machine searching for something. Some signals repeated on a 24-hour cycle, suggesting an unknown biological source. Others were random, fleeting, and mechanical. At first, the Navy assumed these noises came from under-ice movements or distant vessels. Yet many of them originated in regions where no ships could possibly navigate. The sound carried through the dense ice layers, bending and refracting, producing illusions of direction and distance. A single crack could sound like a fleet. To make sense of it, scientists began mapping the Arctic's acoustic layers. Thin sheets of water trapped between ice and pressure ridges that acted like mirrors, reflecting sound across hundreds of kilometers. Within these layers, noise could travel enormous distances, its source lost, its shape distorted. That's when they began calling it the singing ice. Imagine standing on a sheet of frozen sea under the midnight sun. There's no wind, no movement. The horizon glows faintly blue. Yet beneath your feet comes a resonant vibration, deep and melodic, like the breathing of the planet itself. The ice flexes, shifts, then releases its tension with a drawn-out sigh that trembles across the frozen plain. Each sound has its own origin. Pressure ridges groan as the ice plates grind together. Newly forming ice snaps with high-frequency pops, the birth cries of crystals expanding into supercooled water. Seals produce chirps and trills so rapid they resemble the clicks of digital code. And somewhere in the distance, bowhead whales release songs that bounce endlessly beneath the ice, harmonizing with the groans of the shifting flows. Together, they form a complex, ever-changing orchestra. Yet even after decades of study, large portions of that orchestra remain unidentified. One of the most puzzling discoveries came from hydrophones placed under the Beaufort Sea in the 1960s. The recordings revealed a repeating tone, a sharp metallic hum that rose from the depths, climbed through several octaves, then vanished. It occurred at irregular intervals, often during the stillest hours of the polar night. At first, scientists thought it was the cry of bowhead whales, but its pitch was far too stable and its pattern too consistent. It didn't behave like any known animal vocalization. When the recordings were analyzed at the Naval Research Laboratory in Washington, the sound was described as machine-like, though no vessel or submersible matched its profile. It became known simply as the Arctic ping. For years, the ping was forgotten, buried in archives of Cold War data. But in 2016, reports from Inuit hunters near Nunavut brought it back to public attention. They claimed that a strange, persistent hum was echoing through the waters of Fury and Hecla Strait, a sound so loud it seemed to drive away the seals and whales that normally gathered there. Canadian authorities investigated, deploying sonar equipment and divers, but found nothing. No mining, no submarines, no seismic testing. The hum eventually faded, as mysteriously as it began. The parallels to the old Navy recordings were undeniable. And so scientists returned to the question, what exactly is making the Arctic sing? The most accepted explanation points to the ice itself. As temperatures fluctuate, sheets expand and contract, producing vibrations that can resonate across miles. When the wind blows across open lids, narrow cracks of open water, it can set the ice edges vibrating like the reeds of a vast instrument. The result is an eerie, harmonic wail that drifts across the frozen landscape. But this explanation doesn't cover everything. Some tones persist even in calm, windless conditions. Others shift pitch too smoothly to be caused by simple cracking or pressure release. In some cases, the frequencies seem to mimic deliberate modulation, as though the sound were controlled. Could it be biological? Marine biologists studying Arctic soundscapes have long noted that certain animals use frequencies beyond human hearing to communicate beneath the ice. Bearded seals, for instance, emit long, haunting songs that can last over a minute, cascading whistles that echo through the darkness. When these are sped up or shifted in playback, they sound eerily synthetic, like the whir of alien machinery. But even the seals don't explain the full spectrum of sounds. Some originate too deep, far below the zones where marine mammals typically dive. Others occur in midwinter, when most biological activity nearly ceases. Then there are the anomalies. In 2019, a team from the University of Alaska recorded a peculiar signal beneath the Chukchi Sea, a sequence of pulses rising in near-perfect intervals, spaced precisely at 2-second gaps. It lasted for hours, covering a frequency range too wide for any known creature. When they filtered out background noise, the signal resembled sonar, except no vessel was in the region. The team nicknamed it the Northern Beacon. To this day, it remains unexplained. Some researchers suspect that these anomalies may come from deep Earth processes, tremors, methane releases, or shifting permafrost that channel their vibrations upward through the ice. The Arctic seafloor is rich with gas hydrates, frozen lattices of water and methane that can fracture suddenly, releasing bursts of energy. Under certain conditions, these ruptures might resonate like massive organ pipes beneath the ice sheet. Others propose something more subtle: interactions between the ocean's layered water masses. The Arctic is stratified, with fresh meltwater floating atop heavier salt water. As currents move, they create internal waves, invisible undulations that roll through the deep. These can produce infrasonic hums when trapped beneath ice, a phenomenon first observed near Greenland in the 1970s. But none of these theories fully capture the complexity of what hydrophones record. Some sounds remain so pure, so tonal, that they seem almost intentional. And that brings us to one of the stranger interpretations, whispered more often among explorers than in academic papers. The idea that the Arctic ice, in its vastness, may act as an amplifier for something older and deeper. There's a curious pattern found in historic records, reports of metallic or mechanical noises coming from the ice long before modern machinery reached the poles. 19th century whaling logs describe distant bells ringing under the water. Norwegian trappers wrote of chains dragged beneath the floes. And in one case, during the 1930s, a Soviet research team claimed to have heard engines turning beneath the ice, though no ships were within hundreds of miles. At the time, these accounts were dismissed as auditory illusions, sound refractions that made distant noises appear near. Yet some modern recordings replicate the same characteristics: harmonic overtones, rhythmic modulation, and abrupt cessation, as though something switched off. Fringe theorists, often on the edge of mainstream oceanography, have suggested that such signals could be the byproduct of unknown subglacial currents interacting with magnetic fields, creating what's called magnetoacoustic resonance. In simple terms, it's the sound of Earth's own geomagnetic energy vibrating through conductive seawater. If true, the Arctic's song might not come from the ice at all, but from the invisible interplay between planet and pole, a conversation written in sound, echoing through the frozen dark. And yet, the human mind can't help but reach further. To the early Inuit cultures, strange sounds beneath the ice were the voices of Tuangait, spirits that dwelled in the underworld ocean. Some legends describe these beings as ancient intelligences, neither gods nor animals, whose whispers guided the hunt or warned of storms. The sea ice, they said, was their boundary, thin enough for voices to pass through, but strong enough to keep their world contained. Modern science may not share those beliefs, but there's something poetic and disquieting in how both myth and physics converge on the same truth, that the Arctic is alive with unseen forces. When you listen to an Arctic hydrophone playback, the experience borders on eerie. The sound begins low, almost inaudible, a deep, thrumming pulse. Then come the pops and creaks, followed by long metallic sweeps that rise like the wail of wind through steel. Occasionally, a single high note lingers, unwavering, for nearly a minute, before vanishing into silence. Each sound is a clue, a fingerprint of movement, pressure, temperature, and life. Yet the full composition remains beyond interpretation. Somewhere beneath that frozen ceiling, the Earth is speaking. We just haven't learned its language. It's worth remembering that sound, in the Arctic, is more than a phenomenon. It's survival. Narwhals navigate by it. Seals depend on it to find breathing holes. Even ice itself listens, transmitting vibrations across miles so that cracks can relieve pressure before catastrophic failure. Every living thing in that ecosystem has evolved around the conversation of sound. Perhaps that's why the loss of sea ice, now retreating faster than ever, feels like the silencing of an ancient voice. As the ice thins, its ability to carry and shape sound diminishes. The singing ice is fading, and with it, we may be losing a record of one of nature's most intricate symphonies, one that predates humanity, one that has been echoing since the first seas froze. Still, even as it melts, the mystery endures. New sensors deployed in the Fram Strait and the Lincoln Sea continue to pick up unexplained signals, sudden booms that appear without seismic cause, or melodic tones that rise in the dead of winter when nearly all marine life is absent. Each recording adds a new layer to the enigma. Are these simply the last gasps of an ice sheet under stress? The voice of geological forces too vast for us to comprehend? Or something older still? A resonance of the planet's hidden machinery, humming quietly beneath the polar night. Perhaps the Arctic's voice is not meant to be understood at all, only heard briefly before it disappears into history. And so, when the scientists pack their equipment and the last ship drifts south through the thinning ice, the ocean remains, whispering beneath the frozen veil, repeating a song no one can decipher, a song that began long before us, and may continue long after we're gone. Story 2. The impossible under-ice phytoplankton megablooms. And so, when the last ship drifts south through the thinning ice, the instruments fall quiet. But the Arctic does not. Because beneath that frozen veil, beneath the groaning pressure ridges and the long metallic sweeps that made the ice seem alive, there is another kind of voice. Not a sound you can catch with a hydrophone, but a flare of life that appears where we once assumed there was only dim endurance. For a long time, the polar ocean was described in strict seasons. Summer meant open water, sunlight, and the familiar green surge of phytoplankton near the surface. Winter meant a lid of ice and snow, and a slow, dark holding pattern beneath it. The model was tidy, bloom above, dormancy below. And then, in the modern era of under-ice sensors and lucky expeditions, that tidy model began to fray. Researchers sampling beneath intact sea ice started finding blooms, not small scattered traces, but sprawling, dense, chlorophyll-rich layers that suggested phytoplankton were multiplying in enormous numbers while the ceiling above them remained frozen. It was the ocean's most fundamental act, photosynthesis, happening under what should have been a light-blocking roof. Phytoplankton are not a single organism, but a drifting civilization of microscopic life. Diatoms with glassy shells, tiny flagellates that move with hair-thin whips, and countless forms that blur the line between plant and animal. They are the ocean's foundation, taking sunlight and carbon dioxide and turning them into living matter. They fuel the food web. They help shape the chemistry of the sea. They are so small that a bloom can be invisible to the naked eye, until it isn't. The under-ice mega bloom mystery isn't that phytoplankton exist beneath ice at all. It's that they can gather in densities that rival open water blooms, in a place where, for generations, scientists assumed there simply wasn't enough light. To see why this felt almost impossible, picture the Arctic's light as a scarce currency. Ice is not a clean window. It is layered, cracked, and often topped with snow that scatters and absorbs sunlight. Under a thick, snow-covered floe, only a small fraction of surface light survives the journey downward. In that dimness, photosynthesis should be weak and slow. But the Arctic is not one uniform sheet. It is a shifting architecture of ice types and thicknesses. And over recent decades, that architecture has changed. There is more first-year ice, more fractured flows, more thin patches, and more melt ponds. Those shallow pools that collect on the surface in spring and summer, scattered like blue eyes across white terrain. From above, they look harmless. From below, they behave like skylights, and sometimes like lenses, channeling brighter light into the water beneath. In that threshold world, where survival depends on a narrow margin, a small increase in light can flip barely possible into suddenly abundant. A few extra hours of usable light each day, a patch of thin ice drifting over a nutrient-rich shelf, a field of melt ponds forming early, before the ice breaks. The under-ice ocean does not need full daylight to bloom. It needs just enough, sustained long enough, in the right place. But light alone does not create a mega bloom. Phytoplankton are also hungry for nutrients: nitrogen, phosphorus, silica, trace metals. In much of the ocean, nutrients are the true limiting factor. So the story deepens into circulation, the hidden movements beneath the ice that can bring rich water upward or trap it away. As winter loosens its grip, the upper Arctic can become stratified. Fresh meltwater forms a lighter layer at the surface, and that stable layering can hold phytoplankton in the sunlit zone instead of letting them sink. At the same time, currents and winds can push nutrient-rich water up from below, especially over continental shelves and along boundaries where different water masses meet. River plumes can add nutrients from land. The ice itself can release material as it warms. Not only fresh water, but particles and dissolved compounds that have been stored in brine and trapped pockets. When those pieces align, the bloom can ignite like a match struck in a dark room. And yet, if the mechanisms are this understandable, why does the phenomenon still feel elusive? Because the Arctic hides its evidence. Satellites can see surface blooms in open water by their color. Under ice, the signal is sealed away. A bloom can spread beneath a frozen roof with no visible change on the surface. You can stand on a white horizon and have no idea that below your boots, the sea is turning green with living cells. This creates the first unsettling question. Have these blooms always been there, quietly happening in pockets we never sampled? Or are they becoming more common because the ice itself is becoming thinner, more ponded, more permeable to light? There are arguments for both. The ocean has always been opportunistic. Where light leaks through and nutrients are present, life takes advantage. But the scale of some under-ice blooms suggests more than a rare curiosity. It suggests a system that may be reorganizing as the Arctic changes. And the consequences are not simply more life. Timing matters in the polar world. Many creatures evolved around a narrow seasonal pulse. Zooplankton reproduction, fish feeding, seabird migrations, even the patterns of whales. If a major bloom occurs earlier, or beneath ice where grazers cannot access it efficiently, the cascade can shift. A bloom can look like productivity while quietly breaking the synchrony that held an ecosystem together. Then there is the carbon question, a quieter mystery, but a profound one. Phytoplankton draw carbon into living matter. Some of that carbon is recycled near the surface, and some sinks, exporting it downward. Under-ice blooms could alter that balance. A dense bloom that collapses may sink in heavy clumps, delivering carbon to depths and sediments in pulses we don't yet track well. Or it might be consumed rapidly, turning into respiration and chemistry beneath a lid of ice that limits ventilation. Either way, the bloom is not just a biological event. It is part of the planet's machinery. Even the ignition is hard to pin down. Does an under-ice bloom begin gradually as a thin haze of cells doubling in muted light until it becomes undeniable? Or is it triggered by events, storms that fracture flows, sudden leads that form and refreeze, shifts in currents that deliver nutrients, warm pulses that thin ice from below while the surface still looks solid? In a place governed by thresholds, a brief alignment can matter more than a steady trend. The ice itself complicates everything. Sea ice is not sterile. It contains brine channels, tiny networks of salty liquid threading through it like veins. Within those channels live ice algae and microbes. In spring, these communities can stain the underside of the ice with brown-green films. When the ice warms and drains, that material can seed the water below. The under-ice world is not ocean plus lid. It is a layered ecosystem with life in the ice and life beneath it, interacting through cracks and chemistry. And so the discovery of megablooms beneath sea ice does something subtle to our imagination. It forces a re-evaluation of the Arctic's basic rhythm. For centuries, travelers described polar seas as empty. White horizons, silent waters, a landscape that looked hostile to life. Even scientific narratives sometimes treated the ice as a pause button. But what if some of the Arctic's most important biological events unfold out of sight, beneath a roof that makes the surface look still? In that sense, the bloom is less a freak exception than a reminder. The surface is not a trustworthy narrator. Modern tools, drifting floats, Under-ice gliders, moorings that sample through darkness and storm, are starting to reveal a hidden calendar. But the more data arrives, the less the Arctic resembles a simple machine. In some years, blooms that models suggest should occur do not. In other years, blooms appear where the ice seems too thick or too early, or in patterns that fade before anyone can follow their trail. The Arctic keeps offering mechanisms, but not schedules. There are moments, described in field notes with the restraint of professional language, that still read like astonishment. A team drills through ice expecting dark water and modest readings, lowers a sensor package and watches the numbers climb. Chlorophyll rising, light levels higher than expected, the water column thick with particles. Sometimes the bloom is so concentrated that it changes the look of the water in the hole. A faint green cast, as if the sea has been dyed from within. One theory that has gained attention is that these blooms are not simply under ice, but under the right ice. Different ice has different optical personalities. First-year ice can be clearer than older, multi-year ice. Snow depth matters even more than ice thickness. A wind-scoured surface can transmit far more light than a drifted one only a few kilometers away. And melt ponds become moving windows that drift with the pack, brightening some places while leaving others in shadow. Another line of thought focuses on nutrients stored like savings through winter. In parts of the Arctic, especially over shallow shelves, winter mixing can load the upper ocean with nutrients. When spring stratification arrives, it can trap that richness near the surface right when light begins to return. In that situation, a bloom does not need the ice to disappear. It only needs the ice to become porous enough to let workable light through. But even with these explanations, a stubborn uncertainty remains. Under-ice blooms seem to arrive with personalities. Some are dominated by diatoms, silica-armored organisms that can grow fast and sink fast. Others feature smaller cells that linger longer and feed different grazers. The composition matters because it shapes what happens next, whether the bloom is efficiently eaten, whether it collapses and sinks, whether it fuels higher life, or becomes a rain of detritus. And that seafloor story is its own quiet drama. In shallow regions, a sudden export of organic matter can feed benthic communities and alter the balance between life in the water and life on the bottom. Some researchers wonder whether under-ice blooms help explain why certain seafloor ecosystems seem more productive than surface observations alone would suggest. A feast happening under a roof, delivered to the bottom without warning. There is also a human dimension. Northern communities that rely on marine food webs are tied indirectly to these microscopic events. A change in bloom timing or composition can ripple outward in ways that are hard to predict, but deeply felt. And because the Arctic is changing, the question becomes not only curiosity, but concern. What kind of ocean is forming beneath the ice we have left? In the more speculative corners of discussion, some speak of under-ice blooms as the Arctic's hidden rebound, life finding new pathways as the environment transforms. Others see an early warning, a system once governed by predictable seasons becoming governed by thresholds and surprises. Both can be true at once, because the same bloom can nourish and destabilize. To stand on sea ice is to stand on a boundary that is no longer fixed. Beneath you, the water may be quietly blooming. Above you, the sky may look unchanged. And between those worlds, the ice moves, carrying skylights, shadows, and secrets across a living sea. And that is where the mystery lingers. Somewhere beneath a drifting flow, in muted blue twilight, a bloom can ignite without warning. It can spread like a living fog, turning clear water into nourishment. It can feed unseen grazers, alter chemistry across a region, and then vanish, leaving only a spike in an instrument's memory and a question no satellite can answer. Above it all, the ice continues to move, to creak, to sing. The roof remains, the secret garden grows, and we are left wondering how many other Arctic seasons unfold beneath the frozen veil, unseen, and how much of the ocean's true calendar has been quietly turning without us ever noticing. Story 3. The perfectly preserved wrecks under ice. From the unseen gardens beneath the ice, where light bends, blooms rise, and life persists in defiance of reason, our journey drifts now toward another kind of secret held in the frozen deep. A secret not of living things, but of memory itself. For beneath those same seas, entombed in darkness and silence, lie the vessels of those who came before us. Ships that set sail into history and never returned. And yet, in the Arctic, loss doesn't always mean disappearance. Sometimes, the cold keeps its dead. It is here, in the slow, freezing stillness of polar water, that time seems to stop. Wood does not rot. Iron does not rust in the usual way. Canvas, rope, even paper, things meant to crumble, can remain as they were on the day they sank. In this place, the ocean is not a grave. It is an archive, and what it has preserved are stories too intact to be coincidence. The most famous of them begin in the 19th century, when explorers set out to find a navigable path across the top of the world, the elusive Northwest Passage. The Arctic was, to them, the last blank on the map, a white desert between continents, imagined as both treasure and trap. Many ships vanished there, but it is the Franklin expedition that would come to define the Arctic's paradox: destruction intertwined with preservation. In 1845, two British ships, HMS Erebus and HMS Terror, departed England with 129 men aboard. Their mission was simple in statement, but monumental in scope. Chart the final missing section of the Northwest Passage, the maritime route that would connect the Atlantic and Pacific Oceans through Arctic waters. They never returned. For decades, search expeditions combed the ice and found only fragments. A spoon here, a boot there, scraps of cloth, human bones marked with knife cuts. The rest was swallowed by the sea, or so it seemed. Then, in 2014, sonar scans revealed something extraordinary. In a stretch of shallow Arctic water near King William Island, a ship appeared on the monitors, upright, almost whole, resting quietly on the seabed. It was Erebus. 2 years later, Terror was found as well, preserved in near-perfect condition, sitting on the ocean floor as if it had been placed there deliberately. When divers entered the wrecks, they discovered a world sealed in ice and silence. Cabin drawers still held combs, notebooks, and glass bottles half filled with liquid. Dinner plates remained neatly stacked in cupboards. Even the ship's bell was intact, its engraved lettering sharp as the day it was cast. The Arctic, it seemed, had frozen the moment of disaster into permanence. To scientists, the reason is as simple as chemistry. Cold temperatures slow decay to almost nothing. In the Arctic's low oxygen water, the bacteria and wood-boring organisms that devour shipwrecks elsewhere can barely survive. Even centuries-old timbers remain hard and whole. The ice, the darkness, and the depth, Together, they create a vault. But to many, there's something more unsettling about the sight of those vessels. Two ghost ships, perfectly preserved in their tombs of silt and ice. They appear not as ruins, but as time capsules, holding the last breath of an age that believed the world could be conquered by courage and will. The Arctic disagreed. Among the many artifacts recovered was a delicate object, a tin of lemon peel marmalade, sealed and still fragrant after nearly 170 years. Another was a journal, its pages fused but legible, filled with tidy handwriting that documented the monotony of daily life before the end came. Somehow, these things endured when the men themselves did not. The tragedy of Erebus and Terror has long invited theories, both scientific and spectral. Lead poisoning from the tinned food, scurvy, exposure, madness born of isolation and hunger. But the preservation of the ships themselves poses its own quiet riddle. Why did the sea allow them to remain so untouched when other wrecks vanish within decades? Was it the temperature, the salinity, or, as some Inuit oral histories suggest, were the ships intentionally trapped, encased by moving ice and slowly lowered into still water, where the cold would hold them forever? In these northern stories, the Arctic is not simply a force of nature. It is an intelligence, something that chooses what to take and what to keep. And the Franklin ships are not alone. Further east, near Greenland's coast, lies another wreck, one far older yet eerily preserved. The Hansa, a German supply ship lost in 1869 after becoming locked in pack ice. When rediscovered in modern times, explorers found its hull nearly intact, its cargo sealed in the hold as if awaiting retrieval. Wooden barrels still held sawdust-dry grain. Glass bottles clinked faintly in the shifting current. Inside one cabin, the skeleton of a clock sat frozen mid-tick, a moment arrested by frost. Then there are the whaling ships. Hundreds vanished during the 19th century Arctic whaling boom, yet many of their remains remain astonishingly whole. In some, harpoons still rest beside open journals. In others, oil lamps remain half full. Divers who visit describe the sensation as stepping into a room where the crew has only just left. The air replaced by seawater, the light dimmed to eternal dusk. And there are newer examples too. Ships lost not to exploration, but to war. During World War II, the Arctic was a corridor for convoys carrying supplies between Allied ports and the Soviet North. Many of these ships were sunk by submarines or aircraft, and their wrecks, resting in near-freezing darkness, remain eerily pristine. One British vessel, discovered in the Barents Sea, was found with its guns still loaded and its compass frozen mid-spin. The captain's logbook was intact, its ink faint but legible. Even the ship's flags, stored below deck, retained traces of colour, crimson and white shimmering faintly under the diver's light. It is a strange paradox. The same cold that kills also preserves. It erases the living, but archives the evidence of their existence. The Arctic doesn't destroy history, it embalms it. Scientists studying these shipwrecks treat them as time machines, perfectly sealed environments that reveal what life was like aboard in the instant before catastrophe. By analyzing dust, mold, and residue from clothing fibers, they can reconstruct diets, illnesses, and even the atmospheric chemistry of past centuries. Every artifact tells two stories at once: the life it once served, and the silence that has kept it safe ever since. But the preservation is fragile. Climate change is warming Arctic waters at an accelerating rate. The permafrost that once sealed these underwater vaults is beginning to thaw, and microorganisms dormant for centuries are awakening. Already, divers report a fine layer of decay forming on once pristine timbers, a slow reintroduction of time into places that had forgotten it. It raises an unsettling question. If the Arctic is losing its ability to preserve, what happens to the stories it has kept for us? What truths will vanish with the melting ice? There are wrecks still missing, perhaps hundreds. The Jeanette, crushed by ice north of Siberia in 1881, has yet to be located despite modern sonar mapping. So too with the Kolyma and the Karluk, ships that vanished with entire crews aboard. If found, they may be as eerily preserved as the Erebus, or perhaps entirely gone, claimed by the shifting seabed. Some researchers believe that in certain regions, layers of brine, supercooled salt water that sinks below the ice, form natural preserving baths. Objects resting in these layers undergo a kind of mummification, their surfaces sealed against decay. Others point to deep anoxic pockets, places where the water contains almost no oxygen, preventing rust and bacteria from forming at all. In these conditions, even fabric can last for centuries. And then there is a more poetic theory, one whispered among divers and maritime historians. They say the Arctic Sea is a storyteller, that it remembers the human ambition that challenged it and responds by keeping the evidence close, not out of mercy, but out of curiosity, to watch what becomes of us after we are gone. One diver described descending through the murky blue haze above Erebus, flashlight beams flickering across the ship's rail. He said the sight felt wrong, not frightening, but intimate, like stepping into someone else's memory. The air bubbles from his suit clinked against the ironwork and drifted upward like tiny bells. Everything around him was still. No fish, no movement. Only the echo of his breath and the knowledge that, somewhere nearby, human hands had once done the same motions in a world that believed it would never be forgotten. And yet, it was. The longer these wrecks remain sealed in their frozen sanctuaries, the more they complicate our sense of time. They collapse the boundary between past and present. A sailor's wool cap, preserved under ice, looks as new as one dropped yesterday. A cup left on a table appears ready to be picked up again. It's as if the Arctic keeps reminding us that history isn't gone. It's simply waiting beneath the frost, patient as the sea itself. But perhaps the strangest part is what happens when these wrecks are finally disturbed. Divers who retrieve artifacts often report an unexpected sound. A faint creak, a sigh, the release of air trapped for centuries. It's as though the ship exhales when touched, awakening from a long sleep. One scientist compared it to opening a book whose pages have been closed for too long, the sudden whisper of the past escaping into the present. Some Arctic researchers have even proposed that this natural preservation might hold answers to modern scientific questions. In sealed compartments aboard the wrecks, ancient microbes, pollen grains, and even traces of mid-19th century atmospheric soot have been found. By studying them, scientists can glimpse what Earth's climate was like long before accurate measurement began. Data written not in ink, but in ice. The ships, in other words, are floating laboratories frozen in time. Yet beyond all the science, there's a deeper unease. Each discovery is also a disturbance, a crack in the perfect silence that has kept these stories whole. Every artifact lifted from the seabed begins to decay the moment it touches air. The Arctic can preserve, but only as long as it is left alone. Somewhere out there, in the labyrinth of shifting flows, there are still hulls untouched by light. Ships from lost expeditions, fishing boats sealed in ice overnight, research vessels that vanished in storms. Their decks may still bear footprints pressed into frost, their lamps still filled with oil that will never burn. And perhaps, if you could see them now, they would look less like wrecks and more like memories suspended in glass, waiting for an eye to find them. The Arctic holds these things the way a glacier holds air bubbles, small pieces of a vanished world, caught in the slow pulse of frozen time. And as the climate warms, each bubble bursts, each secret escapes. What we are witnessing may be the slow unsealing of the Arctic's archive, one forgotten ship at a time. It makes one wonder, how many stories remain locked beneath the ice? How many more perfectly preserved ghosts wait for technology to catch up, for curiosity to dig deep enough to disturb them? And when they are found, will we be ready for what they have to say? Because sometimes the Arctic does not bury its dead. It keeps them, to remind us that nothing we build, no voyage we begin, is ever truly lost. Only waiting, somewhere under the coldest water on Earth, for someone to look down. And remember, the ice may move, the sea may close, but the archive remains, vast, silent, and alive with what the world has forgotten. And as long as the cold endures, so too will its stories, suspended forever in that fragile space between preservation and decay. Yet as we drift onward, we must ask ourselves, what else lies hidden in that vault of frozen memory? If the Arctic can preserve ships and bones and voices of a vanished age, what else might it be keeping deep below the shifting ice? Things that once lived, or perhaps things that still do. The answers wait in silence, sealed beneath the same frozen roof that hums and groans with its secret song. The Arctic remembers, and it is not done speaking. Story 4. The unusual disappearance of ice island T3. The ice may move, the sea may close, but the archive remains vast, silent, and alive with what the world has forgotten. And yet, there is another way the Arctic keeps its stories. Sometimes it doesn't preserve them like a museum. Sometimes it erases them like a tide. Not with violence, not with a single dramatic moment, but with patience, the kind that only exists at the top of the world, where distances are measured in days of drifting, and silence is thick enough to feel like pressure. Because out here, you can lose more than ships. You can lose an island. In the middle decades of the 20th century, long before satellites made the polar ocean feel small, there was a place that seemed to defy common sense. A man-made outpost set not on land, not on a ship, but on a slab of ice the size of a neighborhood. A floating platform of frozen fresh water, torn from a distant ice shelf, wandering through the Arctic Ocean like a slow, indifferent animal. It was called Ice Island T3, and later it would carry another name, Fletcher's Ice Island. T3 belonged to a strange category of Arctic phenomena, tabular ice islands. Not ordinary sea ice, which forms from salt water and breaks and reforms each season, but thick, ancient ice carved from the great shelves of the Canadian high Arctic. These islands could be dozens of meters thick, with flat tops that looked almost engineered, and walls that dropped straight down into the ocean like cliffs. They could persist for years, even decades, surviving storms and winters that would pulverize thinner flows. For scientists, and for planners who saw the Arctic as a frontier worth understanding, the idea was irresistible. If an island could drift, then an outpost could drift with it. And if an outpost could drift, it could carry instruments into places ships could not reliably reach, into the shifting, hostile center of the Arctic basin. So people built a station on the ice, huts lined up like a small settlement, fuel caches, antennas, instrument shelters, and even runways carved into the surface. Long, straight strips groomed in brutal wind. Planes could land, supplies could be delivered, personnel could come and go. A little world could exist on a piece of ice that was never truly still. And because it was never truly still, it never truly belonged to any one place. T3 drifted with the slow circulations of the Arctic Ocean, caught in currents that loop and spiral, sometimes dragging ice toward the Beaufort Sea, sometimes carrying it across the basin toward the Fram Strait, where ice can be exported into the North Atlantic and dissolve into warmer water. To live on T3 was to live inside motion you could not feel. Day to day, the island's surface was as solid as land. You could walk, build, drill. But in the larger view, the view of weeks and months, the entire station was migrating. Latitude and longitude changed like a slow heartbeat. The horizon stayed the same, but the world beneath your boots was quietly leaving. And then there was the deeper irony. We often think of ice as something that holds, but ice also moves, and ice also breaks. T3 did not vanish like a magic trick. It didn't disappear in a single storm that could be pinned to a date and turned into a neat conclusion. Instead, it began to do something far more unsettling. It became hard to locate, hard to identify, and sometimes hard to prove was still the same object at all. To understand how an island can go missing, you have to step back into that pre-satellite era. Tracking a drifting station meant radio contact, aircraft reconnaissance, reports from ships, and calculations based on drift rates and pressure patterns. It meant a kind of polar bookkeeping, a faith that the Arctic's slow motion could be predicted if you watched the winds and the ice charts carefully enough. But the Arctic is not a tidy system. Whiteout can make an ice island indistinguishable from the pack. Low cloud can ground aircraft for days. Storms can rearrange ice fields like shuffled cards. And an ice island itself can ride low, its top scoured by wind, its edges softened by melt, until from above, it looks like just another pale slab among thousands. Even when you find it, you might not recognize it. Ice islands fracture. They carve smaller pieces. They change shape. They lose corners. They split along old stress lines. An island that was once a clean rectangle can become a jagged, broken polygon. A runway that was once smooth can become a web of cracks. A station that was once here can, in a season, become somewhere near here, because the ice itself has redefined what it is. Over the decades, T3 experienced periods where it was occupied, abandoned, reoccupied, a station that was intermittently alive, then quiet. When people weren't there, the Arctic still was. Snow accumulated and buried traces. Wind sculpted drifts into hard shapes. Metal left behind grew rimed with frost, then corroded in the salt air. And the island kept moving, dragging the memory of human presence with it, like luggage no one remembered packing. At times, reports suggested T3 was lost, not gone in the sense of destroyed, but gone in the sense of unconfirmed. A point on a chart that had drifted beyond reliable contact. A place that existed, theoretically, but could not be reached with certainty. And then, sometimes, it would be found again. A reconnaissance flight would spot a flat-topped slab where none was expected. A radio signal would crackle in, thin and distant, and coordinates would be updated. The lost island would re-enter the human record for a while, before slipping away again. It's tempting to treat this as simple logistics. The Arctic is big, and human attention is small. But the deeper unease comes from what it implies. If you can misplace an island with runways and buildings on it, what else can be misplaced out here? Here, the mystery becomes almost philosophical. The previous story spoke of the Arctic as a time capsule, a place that can preserve wrecks, tools, and human moments in suspended cold. Fletcher's Ice Island suggests the opposite, that the Arctic can dissolve the boundaries of a story until it no longer has an ending you can point to. Because what is a disappearance really, when the thing does not leave behind debris in the conventional way? When it fractures into multiple pieces, each one continuing on its own drift path. When the name T3 ceases to refer to a single object and becomes a lineage, a family of ice with shared ancestry but no single body. Scientists can explain much of this with blunt, elegant physics: stress and strain, thermal expansion, basal melt, and fracture under waves. In some years, long-period swell can penetrate deeper into the pack than expected, flexing tabular ice and opening cracks that propagate silently across kilometers. In other years, warmer water can nibble at the underside of an ice island, thinning it from below until its integrity changes and it becomes easier to break. But even with explanation, the feeling remains. Something solid became uncertain. Something mapped became unmapped. Something inhabited became blank. Imagine flying over the Arctic in those years, scanning for the island. Below you is an endless quilt of white and grey, pressure ridges like frozen waves, leads of black water like cracks in porcelain, faint blue shadows where snow has thinned. Then you see it, a cleaner shape, flatter and more uniform than its surroundings. You circle lower. You recognize the geometry of human work, a straight line that could only be a runway, a cluster of dark dots that might be huts. And yet, no smoke rises, no radio answers. A station without people is a particular kind of silence. It's not the silence of wilderness, it's the silence of abandonment. And as time passes, even abandonment loses definition. Wind tears at loose materials, drifts swallow doorways, antennas tilt, until a crack opens through it, until a storm breaks it, until the thing you are looking for is no longer one thing at all. This is the part the Arctic never announces. Somewhere in a polar night, a fissure forms with a sound like distant gunfire. A hut shifts as the surface subtly warps beneath it. A runway splits into halves that will never meet again. A slab carves away, carrying a fragment of metal and cable into a dark lead, where it disappears under new ice. No catastrophe, just removal. Those who served on drifting stations described the surface as deceptively ordinary. Coffee brewed on a stove while outside the wind polished the snow into a hard glaze. A generator thumped behind a wall. Instruments ticked and recorded. Air temperature, pressure, wind, the slow rise and fall of the ice itself. In winter, the sun could vanish for months, and the station's world would shrink to lamplight, and the narrow corridors people shoveled between buildings so doors wouldn't freeze shut. In summer, the light returned without warmth, lingering low over the horizon for hours, turning melt ponds into blue glass and making the island feel almost like land. Until you heard, beneath the wind, the subtle pops and creaks that reminded you it was still a temporary roof. Joseph Fletcher and other early researchers treated T3 as a rare gift, a way to take the pulse of a region that resisted ships and mocked ground stations. From a drifting island, they could sample the atmosphere and the ocean, Measure magnetism and weather. Watch the ice deform and report back from latitudes that had once been the blank margins of maps. It was science conducted on a surface that was always quietly betraying its own stability. Underneath it all was a constant background tension of stress. Not emotional stress, but mechanical stress, written into the ice like a hidden script. Tabular islands look calm from above, yet they carry old fractures inside them, scars from calving and grounding, from years of flexing. A new crack doesn't always begin at the edge where it's easy to see. It can begin in the center, invisibly, and only announce itself later as a long line that seems to appear overnight. This is how T3 could change identity without anyone deciding it should. A pilot might report a familiar outline, only for a later flight to find the outline altered. One season, the island is a single slab. The next, it is two pieces drifting close together, close enough from altitude to be mistaken for one. In an era of sparse reconnaissance, that difference mattered. The name became a kind of educated hope, a label reaching into fog and insisting there was still a single answer in there to be found. There is also a quieter possibility, one that feels almost too human to admit. In a place like this, losing track can begin as a rounding error, a missed flight, a storm that delays a resupply, a coordinate copied down with a digit wrong, then repeated because the next person trusts the last. Over time, those small slips can widen into real distance until "we last knew where it was" becomes "we think it should be somewhere in this region, and the region is larger than some countries." And when the island is rediscovered, the effect can be strangely intimate. Not like finding a continent, more like finding a forgotten room in your own house. It never stopped existing. You simply stopped visiting it. The Arctic doesn't notice when we stop paying attention, and it doesn't pause its slow edits while we look away. Fletcher's Ice Island forces a final uncomfortable question. If the Arctic can preserve a shipwreck like a sealed room, holding its furniture in cold perfection, and if it can also erase a man-made settlement on a moving island of ice, letting it drift beyond contact and fracture into anonymity, then what decides which stories are kept and which stories are allowed to blur into nothing? Because somewhere out there, under a ceiling of moving flows, there may still be pieces of T3, not labeled, not recognized, not recorded, drifting as pale slabs among countless others. And if an aircraft passed overhead and a camera looked down, it might see nothing more than a clean, flat patch of white. But beneath that white, the Arctic might still be carrying the memory of a runway, a rusted bolt, a buried antenna, a footprint pressed into snow and then sealed under years of accumulation. Not preserved like an artifact in a vault, but preserved like a thought you almost remember. And the next time we look up at the polar map and draw confident lines across a place we rarely see, we might wonder, how many other islands have slipped away like that? Not destroyed, not found, simply unaccounted for, moving quietly through the world's coldest ocean, where even something the size of a city block can become, in time, just another anonymous piece of the drifting white. Story 5. The Gackle Ridge, earthquakes and volcanic activity under permanent ice. But not all mysteries drift on the surface. Sometimes the Arctic hides its secrets in motion, so slow we mistake it for stillness. An ice island that slips out of the record, a runway remembered only as a faint idea beneath accumulating snow. And sometimes, beneath that same white silence, the planet itself is moving in ways that feel impossible to picture. Because under the permanent lid of polar ice, far from any coastline, there is a seam in Earth's crust that never sleeps. It lies across the top of the world, like a scar beneath a bandage. An active mid-ocean ridge in the Eurasian basin, called the Glacial Ridge. On maps, it looks like a thin, confident line. In reality, it is a long, broken mountain range under several kilometers of black water, beneath seasons of ice that can be meters thick, shifting, grinding, closing, and opening like a slow jaw. If you stood above it in winter, if standing above it were even possible, you would see nothing but a pale desert of pressure ridges and blown snow. No smoke, no glow, no warning that below, rocks are tearing apart and magma is finding its way upward, and earthquakes are tapping out signals into an ocean no human eyes are watching. This is one of the strangest tricks the Arctic plays on the imagination. It makes active geology feel like a rumor. Most people learn about volcanoes as things you can see. Cones against the sky, red rivers, ash in daylight. But under the polar pack, volcanism is blind. It doesn't announce itself with spectacle. It announces itself the way a locked room announces a visitor. Through a vibration in the wall, a small change in the air, the feeling that something moved when you weren't looking. And in the deep ocean, that air is water. Dense, pressurized, an excellent carrier of sound. Sound becomes the Arctic's language of hidden events. It travels farther than light. It wraps around mountains. It finds the quiet places and fills them. And this is why the Glacial Ridge matters to a story about under-ice mysteries. Because much of what we know about it doesn't come from seeing it at all. It comes from listening. Listening in the Arctic is not as simple as lowering a microphone over the side of a ship. In many places, there is no side to lower from, only a field of ice that must be treated like temporary land. Crews cut holes, build small shelters against the wind, and thread cables down through slush that freezes as quickly as it is cleared. Instruments are moored beneath the ice for months or years, then recovered in a later season, if the ice allows it, if the mooring has not been dragged away by moving ice or currents. That fragility shapes the entire narrative. A single swarm might be recorded beautifully at one sensor, while another sensor a few hundred kilometers away hears only a faint blur. A plume might be detected as a subtle chemical tilt, just enough to suggest something happened. And then the current carries it away into darkness before anyone can chase it. The Glacial Ridge is a spreading center, a place where two tectonic plates pull apart, and the planet makes new crust to fill the gap. But unlike the faster mid-ocean ridges in warmer oceans, the Glacial Ridge spreads at a painfully slow rate, often described as the slowest spreading ridge on Earth. That slowness is part of the tension. A very slow ridge should, in theory, be starved. Less molten material rising, more cold rock exposed. And yet, in the early 21st century, scientists began detecting hints that the Glacial Ridge could be unexpectedly lively. Earthquake swarms, tremor-like signals, and chemical traces suggesting recent volcanism. Not loud in the dramatic way, but active in a way that keeps ambushing expectation. To grasp how uncanny this feels, picture the environment where these detections happen. Above, the sea ice acts like a moving ceiling. It creaks, it fractures, it slams together in pressure ridges. It produces its own groans and metallic sweeps, sounds that can mimic machines, or distant ships, or something alive. Under that ceiling, the water is layered, cold surface waters, denser deeper waters, invisible boundaries that bend sound the way glass bends light. A single event, a single crack in the crust, can be refracted and carried over enormous distances. So instruments don't receive a clean message. They receive a signature, an acoustic fingerprint smeared by the ocean itself. This is where the ridge becomes more than geology. It becomes an interpreter's puzzle. A hydrophone hears a low-frequency rumble. A seismometer notes a cluster of tremors. Water samples show shifts in chemistry, helium isotopes that hint at mantle sources, or spikes in certain metals, or fine particles that weren't there before. But the ridge is not a laboratory. It is a place where every measurement is an expedition, and every conclusion is provisional. One of the most intriguing traces of undersea volcanic activity is the creation of plumes, clouds of warm, mineral-rich water that rise from the seafloor and drift like underwater weather. On ridges, these can come from hydrothermal vents, where seawater circulates through hot rock and returns infused with chemicals. They can also come from eruptions, when lava meets seawater and fractures rock into tiny glassy shards. In the Arctic, plumes are often detected only indirectly. A faint warmth where none should be, an anomaly in turbidity, an unexpected chemical signature captured by an autonomous instrument moving through darkness. It's the kind of evidence that feels like tracing a fire by the smell of smoke without ever seeing a flame. And there is another layer of strangeness at slow ridges like Gackle. Sometimes the seafloor is not capped by fresh lava at all. The crust can be so thin and magma so intermittent that deep mantle rocks may be exposed and altered by seawater. In that reaction, serpentinization, rock and water generate hydrogen and other compounds, a kind of invisible fuel. It is the deep ocean's version of a fire that burns without flame, feeding microbial ecosystems that never see sunlight and never need it. Life down there can be powered by chemistry alone, thriving in a darkness so complete it feels more like an interior space than a place on Earth. And yet the signs of activity can still be persuasive. Reports of fresh volcanic glass, seismic swarms, and plume-like chemistry have pointed to episodes of recent change along the ridge. Moments when new rock may have been laid down on the seafloor beneath the most inaccessible ocean on Earth. An eruption under the pack does not break the surface like a classic volcano. The water above acts as a lid, and the ice above that acts as another lid, and the pressure is immense. Instead of a plume of ash into sky, there may be a plume of superheated water into cold abyss. Gas bubbles rising until pressure crushes them smaller, and shock waves that move outward as sound. And sometimes it is that sound, the shock wave, the long rumble, the sudden pulse, that becomes the most haunting part of the story. Because in the Arctic, acoustic detection is both powerful and fragile. A sound that resembles a distant explosion could be an undersea landslide. It could be a calving event, a chunk of ice collapsing into the sea. It could be the fracture of a pressure ridge. It could be an earthquake. It could be volcanic activity. In a place where visibility is rare and coverage is thin, the mind is tempted to assign mystery to what might be ordinary, and to miss what is extraordinary. The Gackle Ridge lives in that ambiguity. Consider what an earthquake looks like when you can't see land. On the continents, earthquakes rattle windows and sway buildings. People feel them and mark the moment. Under ice, there is no crowd to remember. There are only instruments and the thin line of interpretation between signal and story. A quake swarm might unfold over hours or days. Dozens, sometimes hundreds, of small earthquakes rippling along a section of the ridge. Individually, each is minor. Together, they suggest a process: plates slipping, crust cracking, perhaps magma intruding like a wedge. In the data, it can look like a fever. From above, you would see none of it. Just a white plain, a drifting flow, and beneath, an entire mountain range shifting in the dark. Some of the ridge's events are carried as T-waves, acoustic waves generated by earthquakes that travel efficiently through the ocean. In a basin where sound can be guided by the water column, a quake in one hidden corner can become a faint pulse in instruments moored far away, like a heartbeat transmitted through water. And sometimes the waveform is strange. Not the clean, sharp onset you expect, but a drawn-out rumble, a sequence of pulses, a tone that seems to sweep. This is where the boundary between known and unknown starts to blur. Not because the cause is supernatural, but because our sensory access is so limited that even natural events arrive distorted. So scientists become archivists of faintness. They compare timestamps. They triangulate. They look for correlation between seismometers and hydrophones and chemical sensors. They search for the coincidence that becomes evidence: an earthquake swarm followed by a plume, a chemical anomaly paired with volcanic glass recovered later, an acoustic event aligned with tremor patterns. But even when those coincidences line up, direct confirmation can take years. Waiting for ice conditions, waiting for a cruise, waiting for the chance to return to the same coordinates and see if the seafloor has changed. By then, the ocean has already carried the plume away. The ridge has already cooled. The moment has passed, leaving behind only an echo in data. This delay is part of what makes the ridge feel haunted. It is always happening earlier, always out of reach, always told in retrospect by instruments that survived long enough to report back. There is also a quieter question: how this hidden ridge might influence the under-ice ocean above it, even in small ways. Hydrothermal activity can seed the deep with minerals and chemicals. Volcanic events can inject fine particles and gases. In some settings, these changes can affect microbial life, alter local water density, and contribute to mixing. In the Arctic, where the water column is strongly layered and the seasonality of light and ice controls so much, even subtle changes can be difficult to observe and easy to argue about. Mainstream science is cautious here, and it should be. But caution does not erase curiosity. It simply keeps the mystery honest. And the speculative mind goes one step further. If the ridge can produce unusual acoustic signatures, pulses that travel long distances, then how many unidentified sounds recorded under polar ice might be the ridge, translated by distance and water layers into something uncanny? A signal mistaken for machinery. A rumble heard as a distant presence. A pattern that seems deliberate simply because geology, when it repeats, can feel like intention. It's a comforting thought. The unknown is still natural. The strange noise has a name. But comfort is not certainty. Some recordings do not match neatly. Some are rare. Some occur in patterns that don't align with known quake catalogues. And in an environment where instrument coverage is sparse, absence of evidence is not evidence of absence. The Arctic's under-ice world is, in many places, still a half-mapped listening room. If Ice Island T3 taught us that even a man-made outpost can slip out of the story, changing shape, blending into the pack, becoming unfindable, then the Gackle Ridge teaches something deeper: that the planet's largest forces can also slip out of the story, not because they are small, but because they are hidden. We tend to believe in what we can photograph. In the Arctic, Belief often has to be earned through indirect traces. The chemistry of a water sample, the microscopic shards of volcanic glass, the time-stamped tremor on a graph. Somewhere under the ice, the ridge is still making new seafloor, quietly, relentlessly, while the surface drifts above it, erasing tracks, collapsing runways, smoothing pressure ridges into anonymous white. And if you could hover in the dark water above that ridge, you might not see lava at all. You might see only darkness, the slow drift of particles, a faint shimmer of warmth, perhaps the brief, ghostly snow of mineral flakes falling back down after a plume. And then, without warning, you might feel a vibration pass through the water. Not loud, not violent, just a signal. A reminder that the Arctic does not only move at the surface, it moves below too. And somewhere in the long archive of under-ice recordings, among the groans of shifting flows and the distant calls of animals, there may be pulses we have already heard, but not yet understood. Not because they are impossible, but because the ridge speaks in a language of echoes, and the ice above is always singing over it. Story 6. Mega iceberg, keel scours, the deep gouges that shouldn't exist. And yet, for all the pulses that travel through Blackwater, those quiet vibrations from the hidden ridge, there is another kind of message the Arctic sends us. One that doesn't arrive as sound at all. It arrives as a scar, not in the ice, but beneath it. On the seafloor, on plains of mud and sand that should be soft, forgetful, easily smoothed by time, there are gouges so long and so deep that they read like handwriting from something vast, heavy, and unstoppable. A record pressed into the Earth's skin and left there in silence, waiting for a ship with the right instruments to pass overhead and notice. These are iceberg keel scours, the furrows carved when the submerged keel of an iceberg, its hidden underside, grinds along the seafloor. In shallow waters, a berg is not a drifting decoration. It is a moving mountain with its roots in the dark. And when that root touches bottom, it becomes a plough. We know scours exist. We expect them. Modern icebergs ground on continental shelves all the time, especially along long, low margins where depth is measured not in miles, but in a few hundred feet. Engineers map scours to protect cables and pipelines. Biologists study them because they reset seafloor habitats like wildfires reset a forest. But the Arctic holds a different class of mark, gashes that do not fit comfortably inside the present. Some scours are immense, tens of kilometers long, cut through compacted sediments like a blade dragged across wax. Some are so deep that, to make them, the iceberg's keel would need to hang far below the surface, deeper than icebergs in today's Arctic are supposed to reach. A normal berg carves from a modern glacier front, floats, melts, and dies. It carries a draft that is large, yes, but still governed by the realities of present-day ice thickness. These scours hint at something else. Not just an iceberg, but a mega iceberg. An iceberg born from an ice sheet in crisis, a slab thick as a skyscraper is tall, wandering out into shallow seas like a displaced continent. To understand why these gouges feel unsettling, you have to remember a simple fact. The part of an iceberg you see is only a fraction of what exists. The white spires and blue caverns above water are the tip in the most literal sense. The rest, often the majority, is submerged. And the deeper the keel, the thicker and more massive the ice must be. A deep scour is not merely a line, it is a measurement. When researchers run multi-beam sonar across an Arctic shelf, they aren't seeing the seafloor with their eyes. They're painting it with sound, sending pulses down, listening to the return, turning echoes into relief. On a screen, the seabed becomes a grayscale landscape. Ripples, dunes, boulders, and, sometimes, something that looks like a trench cut by a giant finger. In certain regions, these features are not subtle. Parallel sets of grooves march across the shelf. Some curve, some intersect, some end abruptly as if the plough lifted. Others begin with a mound of pushed sediment, like the berm at the edge of a tyre track, before stretching on into darkness. And then there are the deepest ones, the tracks that seem to require drafts hundreds of meters deep, implying ice thicknesses that belong not to the Arctic we know, but to an Arctic we have only inferred. Because for an iceberg to carve a gouge at depths that extreme, it must have floated with an underwater draft near that depth. Draft scales with thickness. Thickness points back to source, to the ice shelves and ice streams of the past, to periods when ice sheets were not merely present but expanded, grounded, and capable of calving monsters. This is where the mystery opens, not in the existence of scours, but in what they imply about abruptness. Ice sheets are often pictured as slow, patient, ancient, but the geological record keeps whispering that they can also fail suddenly, that they can rupture, disintegrate, and release fleets of bergs in pulses, events so large they leave signatures far beyond the calving front. In the North Atlantic, sediment layers linked to Heinrich events suggest armadas of icebergs once discharged from collapsing ice sheets, dropping rocky cargo across the seafloor as they melted. Keel scours are like the handwriting that accompanies that fingerprint. They show not just that icebergs existed, but that they were large enough and numerous enough to reshape the seabed. And the Arctic is particularly haunting here because our map of it is still incomplete. Huge portions of the Arctic seafloor remain undersampled at high resolution. Ice, weather, logistics, cost. Everything conspires to keep the region half seen. We have scattered transects of sonar data, a growing archive of under-ice recordings, and long stretches where the story between survey lines is filled in by models and educated guesswork. Only recently have we begun to push mapping tools beneath the ice itself, autonomous vehicles following pre-programmed paths in darkness, their sonar sweeping the bottom while the surface above remains sealed. In those missions, the world is reduced to a thin tether of data. A few hours of battery life, a corridor of mapped seafloor, and then a return to the void. Every new strip of bathymetry feels less like coverage and more like a flashlight beam moving through a cavern. That means there are scours we have not found yet. And when we do find them, we are often looking at the evidence first and building the timeline after. Because a track in mud does not come stamped with a year. Over time, sediments rain down and soften its edges. Currents blur its walls. Organisms rework the surface. Researchers date these features indirectly, by the sediments that fill them, by layers above and below, by correlating forms with known glacial stages and sea level histories. They also account for the shelf itself rising or sinking with isostatic rebound. Earth's slow elastic response after heavy ice disappears, so a gouge that seems too deep today may have been cut in a shallower sea before rebound lifted the shelf and changed the numbers we read off a chart. To tighten that window, scientists need cores, columns of mud taken from inside a scour and from the undisturbed seafloor beside it. The difference between those layers can tell a story of before and after. But cores are expensive under ice, and the Arctic does not hand them out easily. So even with careful work, the date can remain a range, not a point. And in that range lies room for unease. Some of the most dramatic scours suggest not just icebergs, but an ice shelf era. Times when large tabular bergs carved from floating shelves that extended far into what are now open seas. Floating shelves can be hundreds of meters thick. When they fracture, they can release bergs the size of cities, with keels deep enough to scrape the bottom where ordinary bergs would glide safely above. The question becomes, when did the Arctic last have shelves that big? When did it last produce ice thick enough to gouge the seafloor like a plow in deep soil? One possibility points to the last glacial maximum and the chaotic retreat that followed. Another points to older glaciations, times when sea level was lower and grounding lines reached farther across the shelf. Either way, deep scours are a surviving signature of a different Arctic altogether. One where ice did not merely drift on the surface, but occupied the ocean with weight. And there is another layer to the mystery, one that returns us to those under-ice signals. A keel scour is not only a mark of ice, it is a mark of motion. It tells you that something traveled, that it didn't just carve and melt near its birthplace. It drifted through currents and storms and the slow chewing of seawater. And when we see a long gouge that curves or shifts direction, we are watching a past current in disguise. The iceberg becomes a tracer of ancient circulation, its path a frozen arrow pointing into the wind and water of another climate. In some places, scours cluster in patterns that suggest steering, channels where bergs were funneled, bottlenecks where drafts met shallow banks, arcs where a grounded berg pivoted and carved a crescent trench as it swung with the tide. In other places, scours cross in chaotic lattices, as if multiple bergs arrived at once, or as if the ocean briefly became crowded with ice in a violent interval. This is where rare becomes a problem. If deep scours imply mega icebergs, then mega icebergs imply massive calving events. And massive calving events imply that ice sheets can destabilize abruptly, sometimes faster than our comfortable narratives allow. We can describe mechanisms: warm water, undercutting grounding lines, shelves losing their buttressing strength, fractures racing through stressed ice. But the Arctic's scours are a reminder that the end result is not just a model curve. It is a force that physically rearranges the planet. And still, there are cautions. Some researchers argue that what appears too deep can be exaggerated by local conditions. Soft sediments can be overcut, later currents can deepen or sharpen a trough, and uncertain sea level histories can distort draft estimates. Others point out that certain linear features may be made not by drifting icebergs, but by grounded ice streams sliding across the shelf itself during times when the ocean was lower and the shelf was shallow. Even that alternative is unsettling, because it still implies a powerful, mobile ice sheet capable of reaching far offshore and sculpting the seabed. So we are left with a quiet dilemma. The scours are real, the physics is simple, and yet the scale keeps pointing back to episodes of collapse or advance that feel out of proportion to the Arctic we experience today. Imagine one of those events in the moment it happened. A glacial coastline lies far from where it is now. Ice presses toward the sea. At the edge, a floating shelf extends into black water, holding back the weight behind it. Then a fracture runs, fast, loud, final, and a slab of ice miles across separates and begins to drift. Currents take hold. Wind pushes. The berg rotates, its keel rising and falling as it crosses banks. When it grounds, it does not stop like a ship. It presses, it shudders, it plows. The seafloor yields. Sediment piles at the sides. A trench forms that may last for thousands of years. And if that berg is one of many, if dozens, hundreds carve in a short window, then the shelf becomes a moving maze. Some bergs stall and melt in place. Some drift out into the North Atlantic, releasing fresh water and rock, nudging currents, changing climate far away. A gouge on the seabed becomes a local scar with global echoes. What makes the Arctic scours feel uncanny is that they are both familiar and alien. We can explain the process, but the marks imply episodes that, from a human perspective, would feel like the world changing overnight. And the map is still unfinished. Even now, modern surveys sometimes reveal scours where none were expected, patterns that suggest iceberg drafts larger than local sources should provide. Each discovery forces a recalibration. Perhaps icebergs were thicker here. Perhaps sea level was different. Perhaps an ice shelf reached farther. Perhaps we have been underestimating how quickly the Arctic can move. In the modern era, we still see hints of the old behavior in smaller form. Giant ice islands breaking from Arctic ice shelves and drifting for years, stubborn slabs that refuse to melt quickly. They are not the monsters implied by the deepest scours, but they are reminders that thick, tabular ice can exist here, and that when it breaks free, it carries weight below the surface that no photograph can show. In the end, the mystery is not a single trench. It is the sensation of standing on a thin line of knowledge with darkness on both sides. Above, the ice sings. Below, the ridge speaks in echoes. And between them, on the seafloor, the Arctic keeps a quieter archive, one written not in sound, but in carved absence. Lines pressed into mud by ice that no longer exists, pointing back toward collapses we did not witness and timelines we can only bracket. Somewhere beneath the drifting pack, there may be scours we have not yet mapped, deeper, longer, stranger than the ones we know. And if we find them, they will not come with warning. They will simply appear on a sonar screen as a shadowed trench, stretching beyond the limits of the scan, as if something enormous once passed through that place and never looked back. And the unsettling thought is this: the gouge is not just evidence of what the Arctic has done. It is a reminder of what it may still be capable of doing again, quietly, under ice, leaving its next message where we won't hear it, only find it later, carved into the seafloor, like a line drawn by a hand we never saw. Story 7. The underice, death icicles, that grow like living things. They will simply appear on a sonar screen as a shadowed trench, stretching beyond the limits of the scan, as if something enormous once passed through that place and never looked back. And the unsettling thought is this: the gouge is not just evidence of what the Arctic has done. It is a reminder of what it may still be capable of doing again, quietly, under ice, leaving its next message where we won't hear it, only find it later, carved into the seafloor, like a line drawn by a hand we never saw. And if the Arctic can write in scars, if it can press its history into the seabed with the weight of vanished ice, then it can also write in something smaller, something more intimate, not a trench miles long, but a shape you could trace with a gloved finger. A slow, deliberate geometry that forms in darkness and moves like a creature with no mind, yet perfect intent. Because beneath the same roof of ice that hides those colossal keel marks, there is another phenomenon that looks almost impossible the first time you see it. A frozen growth that does not hang from the sky, but descends. A pale, hollow finger that crawls across the seafloor and kills as it goes. A death icicle forming in silence, like a method nature invented when no one was watching. In the polar ocean, winter is not just a season. It's a chemistry experiment stretched across a continent of ice. Seawater freezes differently than fresh water. As crystals form, they reject salt, squeezing it out. That salt becomes brine, water so concentrated it seems to belong to another world. Heavier, denser, colder. A liquid that can still flow at temperatures that would lock ordinary seawater into solid glass. That brine collects in pockets and channels inside the sea ice, little veins trapped between crystals. The ice continues to grow. The brine is pushed downward by gravity and by the slow tightening of the freezing lattice. Eventually, it finds a root, a crack, a weak seam, a narrow chimney that opens like a drain. And then it spills. What happens next feels like an underworld version of a stalactite. The brine emerges from the ice as a stream colder than the surrounding seawater, and because it is denser, it sinks. As it falls, it steals heat from the water around it. The surrounding seawater begins to freeze in contact with this descending thread. A sheath forms around the brine stream, a hollow tube of ice that grows downward as long as the flow continues. It is called a brinicle, and the first time people filmed one, they struggled to describe it without reaching for language normally reserved for living things. It grows, it thickens, it advances. In clear under-ice conditions, a brinicle can look like a translucent vine. It may twist with currents. It may narrow and widen as the brine flow changes. The tube itself is ice, but the center is liquid, brine continuing to pour through its hollow core like blood through a vein. There is something deeply unsettling about that combination. A frozen structure animated by flowing liquid, a skeleton with a pulse, a candle without a flame. And then it reaches the bottom. The seafloor under polar ice is not empty. It is a quiet habitat, slow, sparse, patient. Sea stars creep over sediment like drifting hands. Brittle stars splay their arms like delicate antennas. Small fish hover in the dimness. Everything down there lives on a fragile edge of energy and temperature. Then, one winter, a brinicle arrives. When the hollow ice tube touches down, the brine doesn't stop. It spills out at the base and spreads along the seafloor like a slow flood. Because it is so cold and salty, it freezes the surrounding seawater as it goes, forming a thin layer of ice across the sediment. Anything in its path, anything that cannot move fast enough, is trapped. This is where the nickname comes from. Death Icicle. The footage is haunting. A white finger reaching down from the ice ceiling, contacting the seabed, and then creeping outward, encasing sea stars and small animals in a sudden glaze of ice. Not with a violent snap, but with a patient, methodical advance. The animals do not thrash. They simply become still, as if the temperature of the world has been turned down 1 degree too far. The science is solid. The physics is explainable. And yet the sight of it leaves people with a sensation that is older than reason, like witnessing an execution in slow motion, carried out by a force that never blinks. To understand why, picture the Arctic as layered gradients. Above, air that can be 40 below, wind gnawing at exposed skin. Between, the ice itself, a shifting ceiling, groaning and cracking, sealing the sea away from the sky. Below, sea water that is warmer than the ice, still liquid, still moving, still alive with currents and salt. The brine inside the ice is an anomaly within that system. It is colder than the seawater around it, and it is heavier. When it escapes, it creates a column where the rules are briefly rewritten. Seawater freezing around liquid, a structure forming not because the whole ocean is freezing, but because one stream is extreme enough to freeze what it touches. And that is part of what makes brinicles feel like a mystery, even when the mechanism is clear. How many of them grow each winter across the polar oceans? How often do they form in places we never observe? How frequently do they alter the seafloor in subtle ways, killing one patch of life, freezing one small corridor, leaving patterns in the sediment that persist after the season ends? The Arctic keeps records in quiet mediums, not only in gouges carved by lost megabergs, but in the small graves of creatures caught under a freezing finger. There is also a second layer of intrigue. Brinicles are not just oddities, they are signals, signatures of how ice is forming above, of salinity and temperature profiles, of the hidden architecture of sea ice itself. In other words, they are natural instruments. And like any instrument, they hint at variables we do not fully control. In a strange way, the brinicle is the ocean performing desalination in reverse. When seawater freezes, the ice it creates is comparatively fresh. The salt is exiled, concentrated into brine that has to go somewhere. Over an entire winter, this slow rejection of salt helps form dense water that can sink and drive circulation. It is one of the quiet engines behind polar oceans. Ice forming at the surface, brine descending, water masses rearranging themselves without any visible storm. A brinicle is that engine made visible. Instead of salt dispersing invisibly into the water column, it pours through a single throat. Instead of a diffuse cooling, it becomes a focused blade. Scientists have recreated the effect in controlled settings, chilling saline solutions and watching fingers of ice grow around sinking brine. In the wild, divers have reported brinicles beneath fast ice in places like Antarctica's shallow shelves, where the water is calm enough and clear enough to catch the phenomenon in action. Even then, it can be difficult to predict. The brine channels inside sea ice are not stable pipes. They open, clog, reroute, and collapse as temperature shifts by fractions of a degree. There are subtleties, too, that make the death icicle more than a simple horror clip. The brine inside the tube can be so salty that its freezing point is drastically lowered, which means the brinicle can remain active even when surrounding seawater hovers near its own freezing point. Tiny changes in current can tilt the tube, bending it into arcs that seem almost purposeful. If the flow rate changes, the ice wall thickens or thins, and the whole structure can fracture and heal, layering itself like scar tissue. And then there's what happens after. When the brinicle's cold front freezes a patch of seabed, it can create a thin cap of ice-cemented sediment. That crust can trap gases, alter microbial activity, and change how small organisms burrow and feed. In polar ecosystems where recovery is slow, a brief event can echo for months. Predators that rely on brittle stars find an empty patch. Scavengers gather at the edge. The frozen area becomes a blank tile in a mosaic of life, one more pattern written by winter. It invites an unsettling kind of comparison. The keel scour was a line drawn by catastrophe, an iceberg so massive it belonged to a different climate era. The brinicle is a line drawn by routine. A normal winter process concentrated into a shape that looks unnatural. And that distinction matters because it suggests the Arctic doesn't only change in rare, dramatic collapses. It also changes through quiet mechanics, small episodes repeated thousands of times, unseen. Some researchers have wondered whether traces of brinicle activity might be detectable in seafloor patterns. Tiny frozen runnels, unusual patches of disturbed sediment, localized mortality that appears without obvious cause. But proving it is difficult. The brinicle is temporary. It leaves little behind that is unmistakable. By the time an instrument arrives, the tube may be gone, the crust melted, the animals scavenged, the scene rewritten by currents, which leads to a final, lingering question. How many under-ice phenomena have we only ever met by accident? If a brinicle can exist as a brief, lethal sculpture beneath winter ice, if it can reach down, touch the bottom, and vanish without trace, what else might be happening in the same darkness, in the same cold, with the same ability to erase its own evidence? It's not hard to see why brinicles have become a favorite alien ocean analogy. On worlds like Europa or Enceladus, moons with hidden oceans and icy shells, salt, pressure, and temperature gradients could create their own versions of brine drainage. If an ocean is sealed under ice for millennia, strange structures might grow in the dark, sculpted by chemistry alone. Not monsters, not machines, just physics making shapes that resemble intention. And back here on Earth, under our own polar ice, the brinicle is a reminder that the boundary between the known and the unseen is often just a matter of access. We map the surface, we model the currents, we predict the freeze. But beneath the ice, beneath the ceiling that hides sound and light, there are still moments where the ocean behaves like a secret workshop, assembling something beautiful and lethal, and then sweeping the floor clean. Under ice, normal cues of direction and distance distort. Light behaves strangely. Sounds are both muffled and carried. Your world becomes a ceiling of frozen white and a floor of shadowed sediment, and you are suspended between them like a thought held in the mind of the ocean. Then you see a brinicle descending, something that looks like a limb, a formation that seems to choose a path. It is hard not to feel for a moment as if the ice above is reaching down to touch the bottom. In the language of old seafarers, ice has always carried a kind of agency. It closes, it opens, it grinds, it takes. The brinicle adds a visual to that instinct. Ice that doesn't merely drift, it grows toward you. And because it grows in darkness, it invites the mind to imagine what else might grow there. Some compare brinicles to biological systems, a frozen capillary, a self-assembling conduit, a structure that behaves like an organ. The temptation is understandable. Brinicles blur categories, solid and liquid at once, static and dynamic at once, the product of simple laws that look, from a distance, like intention. But the more grounded unease is perhaps worse, because brinicles remind us how thin the boundary is between a habitable environment and a lethal one. A shift of salinity, a trickle of brine, a brief, localized cascade, and suddenly a section of seafloor becomes an ice trap. In the previous chapter, the seafloor held a trench, a message left by an iceberg that no longer exists. Here, the message is smaller but more intimate, a reminder that the Arctic can reach down as well as press down, that under the ice, there are processes that behave like life, and yet belong entirely to the cold. And if you imagine standing on the frozen surface at night, nothing but black sky and drifting snow, there is a strange comfort in believing that the world beneath is static, asleep, safely sealed away. But the brinicle suggests otherwise. It suggests that beneath your boots, in the dark water you cannot see, something might be growing. Slowly, silently, following a path carved by brine and gravity, descending like a pale finger toward the bottom. And when it touches down, it won't announce itself. It will simply begin to move, quietly, under ice, leaving its own thin line across the seafloor, like a signature written where no one is meant to read it. Story 8. Lake Vostok, the unseen world, under 4 kilometers of ice. There are colder vaults than the seafloor, places where the roof is not drifting ice, but a continent's worth of frozen weight, so thick that liquid water becomes a rumour. After the Binnacle, it's tempting to picture the under-ice world as something alive only in motion. Brine sinking, ice growing, a slow white finger crawling across the bottom like a signature. But Binnacles belong to the sea, connected, in some small way, to tides and weather and the restless breath of the planet. Now we move to an ice that does not breathe. We move inland, away from coasts and horizons, into a place where winter has been uninterrupted for ages. In East Antarctica, on the high plateau, there is a point on the map called Vostok Station. If you stood there, you would see almost nothing at all. No trees, no color, but white and sky. Above you, a hard dome of blue in summer and a black bowl of stars in winter. Below you, 4 kilometers of ice. And below that ice, water. Not a river, not a melt pool, not a seasonal trickle. A lake. Lake Vostok is one of Earth's most isolated bodies of water, sealed beneath the Antarctic ice sheet like a locked chamber beneath a cathedral floor. No one discovered it by shoreline or sparkle. It emerged through remote sensing, radar reflections, gravity hints, the telltale smoothness of ice flowing over something flat and liquid. For years, it existed as a hypothesis, then a certainty, then, inevitably, a temptation. Because if you want to understand what's down there, you have to touch it. You have to sample it. You have to break the seal. And that is where Lake Vostok becomes more than a scientific target. It becomes a moral problem. The water beneath Vostok has likely been separated from the atmosphere for hundreds of thousands of years, perhaps longer. In that time, the surface world changed completely. Ice ages rose and fell. Species appeared and vanished. Human beings arrived and built their first fires and their first cities, while beneath Antarctica, a body of water remained dark, pressurized, and undisturbed. If life exists there, microbial life, the smallest and most stubborn kind, it would have had to adapt to conditions that sound like a dare. No sunlight, enormous pressure, near freezing temperatures, a chemistry shaped not by rain and rivers, but by rock, time, and whatever minerals seep upward from the lake bed. Some scientists picture it as a cold, quiet archive, a low-energy system where microbes, if they exist at all, survive slowly. Cells dividing on a clock that doesn't care about human lifetimes. Others imagine something more dynamic. Lake Vostok is not a puddle trapped under ice. It is large, an inland sea by polar standards, and it sits on a continent that is not dead, only silent. If there are faults beneath it, if there is geothermal heat, then chemical reactions could provide energy without sunlight. The first clues did not come from a direct plunge into the water. They came from accretion ice. At the base of the ice sheet, where the glacier meets the lake, lake water can freeze onto the underside of the ice, layer by layer. That new ice is then carried upward in the slow conveyor belt of the glacier. So, long before anyone could sample the lake itself, scientists could sample the lake's fingerprints, frozen into ice. Accretion ice is a message in a bottle, except the bottle is a continent. It can contain tiny amounts of dissolved minerals, gases, even microscopic particles. In some analyses, it suggested the lake's water may not be uniform, perhaps layered by chemistry and temperature, with zones that mix and zones that stay stubbornly separate. It also produced hints, never clean proof, that biological material might be present, enough to ignite a debate that still shadows every headline. Is it life or contamination? Because contamination is the ghost that haunts Lake Vostok. To drill 4 kilometers through Antarctic ice takes years, and drilling fluid, mixtures used to keep a borehole from freezing shut and to balance pressure. Those fluids and the surface microbes they can carry are the danger. If you puncture the lake carelessly, you risk altering the very environment you want to understand, introducing foreign chemicals and hitchhiking organisms into a world that has been sealed for an age. The tragedy would be subtle. No alarm, no plume, just a silent shift in a place that had stayed unchanged. This is why Lake Vostok has always carried tension. The more we want to know, the more we fear that knowing will ruin it. And yet the pull is obvious. If life can persist beneath kilometers of ice on Earth, it reshapes how we think about hidden oceans elsewhere. Worlds like Europa and Enceladus, where water may exist in darkness beneath thick shells. In that sense, Vostok is not only an Antarctic mystery, it is a rehearsal. The strange thing is that the lake announced itself indirectly long before it had a name. In the 1960s and 70s, aircraft and traversers crossed the plateau, collecting seismic and radar data, reading the ice sheet the way doctors read bone through skin. Certain stretches of ice behaved wrong, too smooth, too reflective, as if the base was not rough bedrock but a polished mirror. By the 1990s, satellite altimetry and improved radar made the picture sharper. A broad, flat region beneath the ice, carrying the signature of liquid water. And once a shape exists, humans begin to plan entrances. At Vostok Station, drilling is less like excavation and more like negotiation with physics. Ice at depth is not brittle. It flows, slowly squeezing like cold wax. Boreholes want to close. Equipment wants to seize. Fluids thicken. Metal contracts. Every technical choice becomes a question of ethics, because every molecule you send down is something the lake has never seen. There is also pressure. Literal, immense pressure. 4 kilometers of ice weighs down like a mountain laid on its side. That pressure lowers water's freezing point slightly and helps keep the lake liquid. But it also means that any opening is not a simple puncture. The lake pushes back. Its water wants to rise, to equalize, to meet the foreign world in the borehole. Then there is chemistry, another kind of pressure. Some models suggest Lake Vostok could be unusually rich in dissolved oxygen because glacial ice contains trapped air, and melting and refreezing can concentrate gases in the water. An oxygen-rich, cold, pressurized lake is a strange combination, potentially hostile to some microbes, potentially energizing to others. If life exists there, it may have had to become not only cold adapted, but chemistry adapted, able to survive oxidants and scarcity at the same time. This is part of why Vostok feels like a locked vault with a complicated lock. Even if you open it, you may not understand the mechanism inside. In recent years, scientists have proposed gentler ways to reach subglacial lakes: clean hot water drilling, sterile melt probes, even autonomous cryobots designed to descend through ice and release a small submersible into the water below. The dream is always the same: a first glimpse that is honest, uncontaminated, undeniable. A camera lowering into black water and showing a reality that does not need interpretation. But dreams are expensive in Antarctica, and every year the ice continues to shift and bury the evidence of our attempts, as if the continent itself prefers the lake to remain a rumor. In 2012, after decades of drilling at Vostok Station, the borehole reached the boundary where ice gives way to lake water. The method relied on pressure, allowing lake water to rise into the borehole and freeze, creating a plug of refrozen lake water that could be retrieved later. It was an attempt to touch the lake without fully opening it. Even then, interpretation became a battlefield. Some analyses reported microbial signatures, DNA fragments suggesting life. Others pointed out how easily DNA appears in laboratories, how persistent contamination can be, how a single stray cell can masquerade as an alien ecosystem when amplified by sequencing. The lake is so difficult to access cleanly that every result seems to carry a shadow attached to it. So what do we actually know? We know the chamber's outline in broad strokes, mapped by radar and gravity. We know there is liquid water, kept from freezing by pressure, geothermal heat, and the insulation of the ice above. We know the ice over the lake flows differently, smoother, as if gliding over glass. We know accretion ice carries chemical hints of what lies beneath. Models suggest the lake may circulate slowly, driven by temperature differences and by melting in some areas and refreezing in others. In the darkness, there may be an internal weather system, water rising, cooling, sinking, movement that never breaks the surface. At the bottom, sediments may lie in undisturbed layers, a record of ashfalls, dust, and the slow grinding of rock. Those sediments could also be food, minerals to be transformed, chemical gradients to be harvested. In the coldest interpretation, Lake Vostok is a museum, a sterile basin where chemistry happens slowly and life is scarce or absent, kept out by the harshness of isolation. In this view, the mystery is the endurance of emptiness. But isolation doesn't always mean death. It can mean specialization. If microbes exist there, they may live in thin films along minerals, clustered where rock meets water, surviving on reactions involving iron, sulfur, hydrogen, energy you can't see, only infer. They might form biofilms on the underside of the ice like invisible gardens. In a closed system, tiny differences can echo for millennia, carving distinct microhabitats inside the lake. There are also unsettling edge cases that scientists mention carefully. Could geothermal hotspots create warmer pockets? Could gases be trapped under pressure in the sediments? Could the lake water hold dissolved gases that behave differently if disturbed? Bubbling, shifting, changing chemistry in a way we have never observed because we have never truly entered. Lake Vostok does not need monsters to be strange. It only needs to be different. And it is different in a way that strains the senses. We can't dive there. We can't easily lower a camera. We know it mostly through indirect evidence, like a planet found by the wobble of a distant star. And indirect evidence breeds stories, even in science. A hidden hydrological network under Antarctica, slow exchanges between basins, dark water moving under white silence. What makes Vostok haunting is that our greatest discovery may be uncertainty itself. We have argued over protocols, over what clean means, over how to sample without turning the first contact into an accident. We have designed probes meant to melt through sterilely, to take only a breath of water and retreat. Because if we make a mistake down there, we may not know for decades. The lake could be altered in a way that looks, in our data, like revelation. Imagine pulling up a sample and finding life, only to realize later it was life you carried down. A ghost story written in DNA. So the lake remains, mostly a locked vault with a thin slit of testimony. Accretion ice, remote sensing, models, a few controversial samples. An unseen world under 4 kilometers of ice, mapped but not met. Some nights at Vostok Station, the wind lays down and the plateau becomes so quiet it feels like the planet has stopped turning. The ice sheet stretches to the horizon and the stars hang above like cold pinholes in a black lid of sky. Under that surface, the lake waits. Not frozen, not flowing toward any ocean, not part of the world we walk through. Just water, held under pressure, insulated by time. And the question that lingers is not simply, is there life down there? It's more personal than that. If we could open the vault cleanly, if we could lower a light into that ancient water without changing it, what would we actually see? A mineral dark emptiness, or a slow ecosystem, unfamiliar and patient, drifting in silence while civilizations rose above. And if something has been living there all this time, cells dividing in the dark while the surface remade itself, would it recognize our intrusion as contact or as contamination? Because in a world sealed for an age, even a single human breath can be invasion. And the most haunting possibility is that the lake will never offer a clear answer at all, that every sample will carry doubt, every discovery will feel, faintly, like we are reading our own signature, written somewhere we were never meant to touch. Beneath 4 kilometers of ice, Lake Vostok remains unseen, a locked room in the heart of Antarctica. And somewhere under that lid, in water that has forgotten the sun, something, whether life or chemistry or nothing at all, continues to exist in perfect darkness, waiting for the moment the seal finally breaks. Story 9. The Svalbard's surging glaciers. Not all mysteries hide in stillness. Some hide in motion, quiet at first, almost ordinary, and then suddenly impossible to ignore. Because ice doesn't only seal and preserve. Sometimes it moves as if it has remembered how to run. From Antarctica's locked vault, we travel north, across oceans and latitudes, into the high Arctic, where the map begins to look unfinished and the land itself seems caught between seasons. Here, on the fringes of Norway's farthest reaches, Svalbard rises from the sea like a shattered crown. Black mountains, pale plateaus, and valleys filled with ice that has been piling up for thousands of years. In winter, darkness can feel like a physical thing. In summer, the sun refuses to set, circling the horizon like a watchful eye. And in that strange light, the glaciers reveal a behavior that still unsettles the scientists who study them. Because some of Svalbard's glaciers don't simply melt or retreat, they surge. For years, sometimes decades, they can appear calm, almost asleep. Snow accumulates in high basins, compacting into firn, then into blue ice, layer after layer, like pages pressed into stone. Down valley, the ice creeps forward at a pace you could measure with a line of stakes and a patient notebook. The kind of movement that feels predictable, even comforting. Nature doing what it has always done. And then, without warning, the glacier lunges. What had been a slow, steady river becomes a rush. The ice accelerates, sometimes by orders of magnitude, charging down its valley, buckling and tearing, pushing its snout forward as if something underneath has released a brake. Crevasses open like fresh wounds. The surface collapses into chaotic blocks and ridges, jumbled ice seracs that look less like geology and more like wreckage. The glacier's front can advance hundreds of meters, even kilometers, in a comparatively short span. And then, just as strangely, it slows again. The glacier returns to its quiet creep, as if nothing happened, as if the lunge was a dream. This is the unsettling rhythm of surging glaciers, a cycle of long stillness, sudden violence, and renewed calm. And the most frustrating part is that surges are not simply fast glaciers. They're a different mode of existence, one that seems to switch on and off. Svalbard is one of the great natural laboratories for this phenomenon. A surprisingly large fraction of its glaciers have surged in recorded history, leaving behind folded moraines like frozen waves and broad, bulldozed forefields where the ice once thrust forward. Even if you arrive after the surge has ended, the land remembers. To understand why this is so strange, you have to imagine what a glacier really is. Not a static block of ice, but an engine made of weight and time. A glacier forms where more snow falls than melts, year after year, building a reservoir that compacts under its own mass. Gravity does the rest. The glacier flows downhill, driven by the pressure of its own thickness. But it doesn't flow like water. It flows by deformation, ice crystals slowly rearranging, and by sliding, when conditions at the bed allow the whole mass to move over rock or sediment. Most glaciers, even in the Arctic, behave in ways that are at least somewhat legible. Warm summers bring more melt. Cold winters slow the surface. Long-term shifts alter the balance between accumulation and loss. But surges don't neatly follow those patterns. They can happen in cold years or warm ones. They can occur on neighbouring glaciers while others remain placid. They can begin without a dramatic external trigger, and they are notoriously hard to forecast. So what flips the switch? The leading explanations live at the glacier's base, where no one can easily watch. The bed is hidden under hundreds of meters of ice. It's cold, dark, under immense pressure, and yet it may be the most changeable place of all. One idea focuses on water. Liquid water at the base of a glacier is like oil in a machine. It can reduce friction, it can lift the ice slightly off the bed, and it can change suddenly from a well-drained system to a clogged one. Imagine a glacier with a network of channels beneath it, tiny rivers pressed between ice and rock. If those channels are efficient, meltwater drains away, and the ice remains relatively stuck to its bed. But if the drainage system collapses, if channels close under pressure or become blocked by debris, the water pressure can rise. And when basal water pressure rises high enough, the glacier can partially decouple from its bed. Friction drops, sliding speeds up. The glacier surges forward. On paper, it's elegant. In reality, it's messy. Because water in the high Arctic doesn't behave like water in temperate mountains. Some Svalbard glaciers are polythermal, part of their base frozen to bedrock, part at the melting point. That means zones of sticky, frozen contact beside zones of lubricated sliding. A surge may be a chain reaction, starting where the bed is warm and spreading as stress reorganizes through the ice. It may involve water stored not in open channels, but in porous sediment, like a sponge beneath the glacier. And it may depend not just on how much water exists, but on where it's trapped, how quickly it can escape, and how the ice reshapes the plumbing as it moves. Another theory focuses on sediment, the deforming bed model. Many Svalbard glaciers rest on thick layers of soft, water-rich till. Under normal flow, the till may hold the glacier back like a stiff paste. But if poor water pressure rises, the till can weaken dramatically. It begins to shear and deform, turning the glacier's base into a moving carpet. In this view, a surge is not a slippery moment, but a structural failure, an entire foundation giving way. There is also thermal switching, the possibility that a glacier's base can transition from mostly frozen to partly thawed over time. As ice thickens in the upper basin, insulation improves. Geothermal heat, small but constant, accumulates. Frictional heating adds a little more. Eventually, a portion of the base reaches the melting point, creating new water and new lubrication. The glacier becomes capable of rapid sliding, and once it does, the surge can propagate down glacier. But even these explanations don't satisfy the question that keeps returning like a pulse. Why this glacier? Why this year? Svalbard offers contradictions. Some surges begin in winter, when surface melt is minimal, suggesting the key water is not from summer warmth, but from older stores, pressurized reservoirs, or water generated internally. Some surges happen even as the climate warms and glaciers thin, which should reduce basal pressure. Other glaciers with similar geometry never surge at all. It's as if each glacier has its own threshold, hidden under the ice like a latch that only occasionally clicks open. To chase the mystery, researchers watch from every angle they can. They place GPS units on the surface, recording movement that can jump from centimeters per day to meters per day. They use satellites to measure subtle changes in elevation and velocity. They listen for ice quakes, seismic snaps from crevasse formation and basal slip. And in a few places, they drill boreholes, lowering sensors to taste pressure and temperature in the unseen bed. What they often find is a story told in delays. Before a surge, the upper glacier may thicken, ice piling up like money in a savings account. The lower glacier may thin and slow, starved of new ice. Stress builds along the length, like tension in a stretched rope. Then the balance tips. The stored ice is released in one intense episode. The glacier spends decades of accumulation in a few short years. A redistribution event that leaves behind a landscape of compressed time. For anyone who returns to the same valley year after year, a surge can feel like the land has moved while you slept. A familiar cliff face no longer aligns with the ice margin. A meltwater stream has been rerouted. A moraine that once marked the edge is now buried. The surface looks newly broken, as if an earthquake passed through it. And in Svalbard, a surge can even threaten roads, research camps, or old mining traces. Quiet reminders that slow ice is not always safe ice. Yet the deeper mystery isn't just hazard. It's what surges imply about glaciers themselves. We tend to treat them as climate indicators and long-term archives, slow recorders of snowfall, temperature, and time. A surging glacier interrupts that story. It is not merely responding, it is reorganizing. An abrupt expression of hidden anatomy. Across Svalbard, old photographs show ice fronts far beyond today's margins. Maps hint at former positions that feel impossible now. And in the forefields lie surge moraines, wrinkled and folded like the edge of a rug pushed across a floor. They are proof that the ice once behaved differently. Proof that the land is not merely melting and retreating, but occasionally lurching. Which raises an uneasy question for the present era. As the Arctic warms, glaciers thin. The surface becomes more melt-prone. Does that make surges more likely by adding water that can penetrate and pressurize the bed? Or less likely by reducing thickness and the pressure needed to activate basal sliding? Could some glaciers be entering a final phase where surges become their last dramatic act? One more release of stored mass before the reservoir is gone? Or could warming create new, unstable plumbing, turning once stable glaciers into potential surges? Right now, the honest answer is, it depends. And that answer is a kind of darkness, because it depends means the system has too many hidden variables. It means prediction is still fragile. If you stand on Svalbard in late summer, with the sun low but refusing to set, you can hear meltwater running under snow bridges, a sound like distant whispering. You can watch a tide waterfront carve into a fjord, chunks breaking off with slow thunder, sending ripples that shatter the mountain's reflection. Everything looks calm. Even the word glacier feels too soft for the idea of speed. And yet, under that calm surface, the base is negotiating with gravity. Water is pressurizing, or draining, or becoming trapped. Sediment is stiffening, or weakening, or beginning to shear. Thermal zones are migrating, millimeter by millimeter. Stress is building in places no camera can see. Then, one winter, the satellite plots begin to change. Velocity arrows lengthen. The ice surface lowers in the upper basin and rises down valley, as if the glacier is pouring itself forward. Crevasse patterns sharpen, and the researchers who have watched for years feel that quiet, uneasy thrill, the recognition that the ice has entered its other life. A surge is not the glacier melting faster. It is the glacier moving faster. Stored ice relocating like a decision. Not supernatural, just unnerving in the way any hidden mechanism is unnerving when it finally snaps into motion. Because if a glacier can accelerate without warning, then its future position is not a simple line on a graph. It is a question about what is happening beneath the ice, and what else is happening beneath the ice that we haven't thought to measure yet. Lake Vostok was a locked room, a sealed place where answers may forever carry contamination and doubt. Svalbard's surging glaciers are a different kind of locked room, one whose door occasionally bursts open, not to reveal what's inside, but to remind us that something inside has been building pressure all along. And when the surge ends, when the glacier returns to its slow creep, the valley looks like it has survived an argument. Moraines are twisted, ice is broken into restless geometry, streams run in new grooves. The landscape holds the evidence, but not the motive. So the question remains, hovering in the polar air like a sound you can't locate. If we can't reliably predict when a glacier will surge, if we can't always tell which ones are close to tipping, then what exactly are we missing beneath the ice? Because somewhere in Svalbard, right now, a glacier may be quiet, its surface smooth enough to cross, its creeks softened by snow. But under that silence, the bed may already be changing. Water gathering, sediment loosening, heat inching upward. And if the switch flips tonight, or next winter, or a decade from now, the glacier will not announce it ahead of time. It will simply begin to run, as if the Arctic, after all its long stillness, still remembers how to move, and chooses, without explanation, the moment to prove it. Story 10. The Beaufort Gyre. A glacier's surge is a kind of sudden confession. Years of quiet pressure, stored invisibly in cold ice and buried water, released in a run that no one can schedule and no one can fully explain. But Svalbard's lesson is larger than any single valley of ice. Because the Arctic doesn't only hide motion inside glaciers, sometimes it hides it inside water, inside whole basins, inside slow, patient systems that don't look dramatic until the day they become unavoidable. And if a surging glacier is the Arctic remembering how to move, then the Beaufort Gyre is the Arctic remembering how to hold. Not a river you can point to, not a current you can watch with the naked eye, but a vast, rotating reservoir of fresh water, gathered and piled beneath a lid of sea ice, turning year after year in the darkness and the pale light, quietly reshaping the balance of an entire ocean. It sits in the Western Arctic, north of Alaska and Canada, where the sea feels less like open water and more like a sealed room. For much of the year, ice covers the surface like a heavy door. Above it, winds circle in broad patterns, and those winds, persistent, invisible, almost casual, press on the ice, and the ice presses on the ocean. Over time, that pressure doesn't just stir the surface, it changes the shape of the sea. The Beaufort Gyre is, in its simplest description, a wind-driven swirl. Under anticyclonic winds, winds rotating clockwise around a high-pressure system, the surface waters are pushed inward by the physics of the spinning Earth. Oceanographers call it Ekman transport. In the Northern Hemisphere, wind-driven flow tends to angle to the right, and across a broad rotating field, to the right becomes toward the center. So the Beaufort Gyre becomes a kind of collection bowl. Fresh water enters the Arctic from many sources. Giant rivers like the Mackenzie, the Yukon, and the Siberian rivers farther west. Precipitation falling directly into the ocean. Melting sea ice, and inflow from the Pacific through the Bering Strait, which carries comparatively fresh water northward. Salty Atlantic water also enters through gateways like Fram Strait and the Barents Sea, but in the Arctic, it often sinks below a lighter cap of fresher water. And that cap matters. Fresh water is buoyant. It floats above denser salt water, creating stratification, layers that resist mixing like oil, and water refusing to become one. In the Arctic, this layering helps maintain the halocline, a boundary zone that can insulate sea ice from the warmer Atlantic-derived water below. It's one of the reasons the Arctic can keep ice at all, even when heat exists underneath. Now imagine that fresh water not as a thin film, but as a pile. In the Beaufort Gyre, the constant inward push can dome the surface, raising sea level in the center by tens of centimeters compared to the edges. Not a dome you'd see from a ship's deck, but one satellites can measure, and one that reveals something eerie, a body of water being stored like a compressed spring. Because when you pile fresh water into the center of a gyre, you are storing not just water, but potential energy. You are creating a system that depends on continued wind patterns and continued ice conditions to keep holding its shape. And scientists have watched that storage grow. For decades, the Beaufort Gyre has been studied with drifting buoys, under ice moorings, ice-tethered profilers that climb and dive through the water column, and satellites that read the ocean's subtle bulges and hollows from space. The record they've built suggests that, in recent years, the gyre has accumulated an unusually large volume of fresh water, an amount often described in terms that sound abstract until you try to picture them. Thousands of cubic kilometers, enough to alter salinity far beyond the Arctic if released in a concentrated pulse. This is where the story turns from geography to suspense. because a reservoir is only comforting when you trust the dam. The dam, in this case, is not concrete. It's a dance between wind, ice, and circulation. The Beaufort Gyre strengthens when the atmospheric pattern favours a stable high-pressure system over the Western Arctic, often linked to phases of the Arctic Oscillation and other large-scale climate modes. Under those conditions, the clockwise wind field tends to persist, the ice is pushed and rotated, and the freshwater stays corralled. But the Arctic is changing its surface rules. Sea ice is thinner than it used to be. It breaks more easily. It drifts differently. In some seasons and regions, it's absent altogether, leaving open water where an ice lid once muffled and mediated the transfer of wind energy into the ocean. That sounds, at first, like it should simply let the wind stir things more strongly, more mixing, more chaos. Yet paradox lives here. Sea ice can act like a grip, a rough layer that allows wind stress to be transmitted efficiently across a broad area. Open water can transmit wind too, but the way the stress spreads, the way turbulence forms, the way storms imprint themselves on the ocean can change. With less ice, the system may become more episodic, less of a steady hand turning the gyre, more of a series of punches from passing storms. Some researchers have asked whether a seasonally ice-free Beaufort Sea would keep the gyre stable, or whether it would weaken it, allowing the freshwater dome to relax outward. Others focus on the opposite risk, that changing winds and reduced ice could sometimes spin the gyre up faster, piling freshwater higher, until it becomes more precarious, not less. And then there is the question that keeps returning, quietly, like a refrain beneath the data. What happens if the gyre lets go? The Arctic is not a closed bowl. It is connected to the North Atlantic through narrow gateways, through the Canadian Arctic archipelago, through Fram Strait between Greenland and Svalbard, and through other channels that act like valves in a global machine. If a large freshwater release were to occur, it would not look like a wave you can photograph. It would look like a change in taste, an ocean slowly losing its salt. It would drift as a lens of low salinity water, spreading and diluting, but still capable of altering how dense water forms in the North Atlantic. And dense water formation is one of the engines of the planet's circulation. In the North Atlantic, cold, salty water can become heavy enough to sink, helping drive the Atlantic meridional overturning circulation, often described imperfectly but memorably as part of the ocean's conveyor belt. Add fresh water and you make surface waters lighter. You can slow sinking. You can change where deep water forms, or how often, or how vigorously. You can shift heat transport, weather patterns, sea level along coastlines, ecosystems that evolved under older, saltier expectations. The science here is careful, cautious, and full of caveats. No responsible researcher claims a single pulse from the Beaufort Gyre will flip a global switch like a movie plot. But the uncertainty is the point, because the Beaufort Gyre is a place where the system's behavior depends on thresholds that are hard to test. You cannot run an experiment where you turn the Arctic winds clockwise for 20 years and then reverse them just to see what happens. You can only observe, model, infer, wait. And the Arctic has a habit of not waiting politely. One of the unsettling ideas is that the gyre's release might not be smooth. The fresh water could drain gradually, leaking out with shifting winds, exporting a little more one year, a little less the next, like a reservoir with a controlled spillway. But another possibility, the one that makes this feel like a slow burn suspense story, is abrupt relaxation. If the atmospheric circulation flips into a pattern that favors cyclonic winds over the Beaufort region, The direction of the stress changes. The inward push can weaken or reverse. The dome can flatten. The fresh water can spread outward toward the boundaries of the basin, where currents and straits can begin escorting it out of the Arctic. Even if the change is not a single dramatic dump, it can still behave like a regime shift, a different default state, a different set of pathways, a different rhythm of export. And in the Arctic, regime shifts are the real cliff edges, not a single event, but a new normal that makes old predictions irrelevant. To make it stranger, the gyre is not only storing fresh water, it is storing memory. Freshwater content and stratification shape the under-ice environment for life. How nutrients move upward, how plankton blooms ignite or fail, how oxygen and carbon cycle through layers. A stronger freshwater cap can suppress mixing, limiting nutrient resupply to surface waters, altering the timing and intensity of biological productivity. It can shift where certain species thrive, where others retreat. It can change sound propagation under ice. It can change the very texture of the Arctic Ocean as a habitat. So when we talk about the Beaufort Gyre's unknown tipping points, we aren't only talking about climate models and circulation charts. We're talking about an ecosystem balanced on density differences so subtle they can be changed by a few parts per thousand of salt. We are talking about an ocean that can be reorganized without anyone hearing a crash. And this is what makes the Beaufort Gyre feel almost philosophical, like the Arctic's quieter counterpart to a glacier surge. A surging glacier announces itself with broken ice, crevasses, collapsing seracs, rivers of meltwater carving sudden channels. The Beaufort Gyre announces itself with numbers, salinity profiles, sea surface height anomalies, freshwater inventories tracked like a bank account. But both are stories of stored pressure. Both are stories of forces held out of sight until the moment they move. And both force us into a particular kind of humility, the recognition that prediction is not the same as understanding. We can watch the gyre with satellites. We can map its bulge. We can lower instruments through holes in ice and read the layering like the rings of a tree. We can run models that simulate wind fields, ice drift, ocean currents, freshwater fluxes. We can even replay the past, years when patterns shifted, when the Arctic oscillation changed sign, when freshwater export increased through one gateway and decreased through another. But the future is a different material, because the Arctic is not changing in one dimension. Winds are shifting, ice is thinning, river discharge is changing, storm tracks are evolving, the Pacific inflow varies. The Atlantic layer carries heat that doesn't always stay politely below. Feedback loops, albedo, cloud cover, ocean heat uptake intertwine. The Beaufort Gyre sits inside that complexity like a hidden flywheel. A freshwater dome under ice, held by patterns that might not hold forever. And so the question becomes less, will it release? And more, how does it release in a world that no longer resembles the world that built it? Does a warmer, stormier Arctic shake the dome loose in fits and starts, short pulses that disperse before they matter? Or does it set the stage for a broader rearrangement, exporting fresh water in a way that lingers, accumulating effects far downstream? Does the gyre weaken as ice retreats, losing the mechanism that helped corral the water? Or does it intensify for a time, spinning faster over open water, hoarding fresh water until the imbalance is too large to maintain? And if the release comes, will we recognize it as a moment, or only as a slow alteration of the Atlantic's taste, an invisible dilution that, years later, we trace backward like a scent to its source? There is a particular eeriness to Arctic mysteries like this one, because they are not dramatic in human time. They are patient. They are measured in seasons, in wind regimes, in decades of accumulation. Yet the consequences, if thresholds are crossed, can arrive faster than the build-up suggests. A calm surface, a subtle dome, a hidden load-bearing system, and somewhere beneath winter ice, beneath the scrape of flows and the long night's silence, the Beaufort Gyre continues to rotate, carrying its fresh water like a secret it has not decided to tell. Not yet. But the Arctic has already shown us, through surging glaciers and thinning ice, that quiet does not mean stable. Sometimes quiet means stored. Sometimes it means waiting. And when the winds finally change, when the ice lid weakens just enough, when the dome relaxes and the fresh water begins to slip outward through the Arctic's narrow doors, we may not hear it happen at all. We may only notice, far away, that the ocean has become slightly less salty, and wonder what else, under the ice, has been holding its breath. Story 11. Subglacial lakes in Greenland. The hidden reservoirs that appear, then vanish. The Arctic has already shown us, through surging glaciers and thinning ice, that quiet does not mean stable. Sometimes quiet means stored. Sometimes it means waiting. And when the winds finally change, when the ice lid weakens just enough, when the dome relaxes and the fresh water begins to slip outward through the Arctic's narrow doors, we may not hear it happen at all. We may only notice, far away, that the ocean has become slightly less salty, and wonder what else, under the ice, has been holding its breath. Because the Beaufort Gyre is not the only place the Arctic hides its water. It is simply the one we can picture most easily. A slow, rotating bowl, a dome held in place by winds. But travel east toward Greenland, and the storage becomes stranger. Here the reservoir is not an open ocean beneath a moving lid. It is inside the ice itself, beneath kilometers of it, sealed away in darkness, pressure, and time. Greenland's ice sheet looks, from space, like stillness made visible. A white continent draped over rock, smooth in places, fractured in others, striped with faint wind patterns like fingerprints. But this is not a frozen statue. It is a heavy, shifting body, thick enough to press the crust downward and warm enough in its depths to create melt where, at the surface, nothing seems capable of melting at all. When we picture a lake, we imagine sky reflected on water, reeds at the edge, insects skating over a surface that listens to wind. A subglacial lake is the opposite of that image. No sky, no shoreline you can walk to, no open surface. It is water imprisoned under ice so thick it turns sound dull and makes light irrelevant. And it exists because pressure and heat quietly rewrite familiar rules. Under a deep ice sheet, the weight is immense, so immense that the melting point of ice shifts downward. Add a steady trickle of geothermal heat from the rock below and frictional heat from moving ice above, and you get meltwater that has nowhere to go except sideways, searching for hollows, pooling where the bed allows it, waiting for a route to open. For decades, Antarctica stole the spotlight. Its subglacial lakes became legends with coordinates. Lake Vostok, Lake Whillans, names that sounded like locked doors. Greenland, by comparison, was assumed to be too steep, too fast, too sloped for water to gather quietly. And yet, when scientists began to look through Greenland's ice with ice-penetrating radar, the way ultrasound reads a hidden anatomy, bright echoes started appearing. Flat, mirror-like returns suggesting something smooth and reflective at the base of the ice. Radar does not give you a photograph. It gives you a language of reflections, a pulse sent downward, returning as a signal shaped by what it touched. A sharp, clean, specular return, like light off glass, often points to a boundary between ice and liquid water. But in Greenland, the most unsettling evidence didn't arrive only as bright lines on radar plots. It arrived as the ice surface itself began to behave like a ceiling over a filling room. Satellites that measure elevation, patient, mechanical observers, started noticing broad swells in the ice. Not dramatic hills, not ridges thrown up by storms, but gentle domes rising over months to years. Imagine standing on a plateau of snow, hearing nothing but wind, and feeling under your boots a continent that is subtly lifting by a meter, sometimes two, over an area that would take hours to cross. No fountain, no visible crack, no surface lake, just the geometry changing, recorded by laser altimeters and radar altimeters that return again and again, measuring the same swaths of ice with a devotion no field season could match. And then, sometimes, those domes would collapse. The surface would drop. Not gradually, not like summer melt trickling away, but in a pattern that suggested something beneath had moved, and moved quickly. A reservoir had emptied. A plug had been pulled in a place no human eye has ever seen. This is where Greenland's subglacial lakes become more than a curiosity. They become a mystery of plumbing, an under-ice hydraulic system that can hold water quietly for years, then release it suddenly through channels no one can see, channels that might not even exist until the moment the water forces them into being. The hidden reservoirs that appear, then vanish. Under ice, water is not passive. It is a tool. It reduces friction between the glacier and its bed, allowing the entire mass to slide differently, sometimes faster, sometimes more smoothly, sometimes with sudden jerks. It can spread as a pressurized sheet that lifts the ice like a hand under fabric. It can carve tunnels into ice, cut into soft sediment, and exploit weaknesses in bedrock. In Greenland, where outlet glaciers already race toward the sea, a sudden pulse of basal water can change speed like a sudden shift in temperament. An outlet glacier that was merely fast becomes faster. A sheer margin sharpens. A crevasse field spreads as if the ice is exhaling stress. One of the eeriest aspects is that these lakes can appear, at least appear to us, without an obvious surface cause. A region that looked stable in older radar profiles and elevation records will, within a season or two, show swelling as if a hidden basin is being filled. The water has to come from somewhere. Surface meltwater funneling into moulins, vertical shafts that swallow rivers, or melt generated at the base by friction and geothermal heat. Yet the timing often refuses to align with neat expectations. Sometimes the surface is already cooling toward winter when the swelling becomes most obvious, as if the system below is living on a different calendar. Then comes the vanishing. Drainage events can unfold over days to weeks. The surface lowering, stress patterns shifting, downstream flow speeds changing. In some cases, the water's exit is hinted at near the coast. Subglacial discharge that pours into fjords and turns the seawater milky, or pulses that emerge at a glacier's front like breath from a submerged mouth. In other cases, the path is inferred rather than witnessed. We see the before and after. The middle, the actual journey of the water through the dark, is hidden. So what triggers the plug to pull? the mainstream physics offers several suspects, and none of them feels complete on its own. One possibility is pressure thresholds. As a subglacial lake fills, water pressure rises until it overcomes the strength of an ice dam or a sediment barrier, forcing open a pathway toward a lower pressure region. Another is thermal change. A slight warming at the bed, perhaps from increased friction as the glacier speeds up, could soften basal ice, lowering resistance and allowing a channel to form. Researchers also debate the character of the drainage itself, whether the system flips from a dispersed film of water spread across the bed to a few efficient channels that act like arteries, suddenly relieving pressure and changing the glacier's grip. There is also the possibility of stress and fracture. Greenland's ice is not a uniform slab. It is riddled with weaknesses. If the ice above a lake shifts, due to seasonal acceleration, tidal flexing near the margin, or the slow push and pull of internal deformation, it might crack in just the right way to connect water to a lower pressure corridor. Under such conditions, water doesn't merely flow, it propagates. Pressurized water can force cracks to extend, punching pathways through ice in a process that resembles hydrofracture on a scale that feels almost impossible to picture. Water prying open ice with nothing but pressure. And bedrock matters more than we like to admit, because Greenland's ice sheet is not sitting on a smooth bowl. It rests on mountains, basins, ancient valleys, and soft sediments left behind by older ice ages. In some regions, the bed forms natural hollows where water can pond, subglacial bathtubs carved by deep time. In others, the bed is permeable, and water might store not as a clean lake, but as a saturated layer of sediment, a subglacial sponge. A bright radar reflection can be honest and still be ambiguous because water under ice does not always behave like a clean, open pool. It can spread thin, it can infiltrate, it can hide in texture. The hidden reservoirs that appear, then vanish. This is where the mystery deepens, because our instruments, powerful as they are, still infer more than they witness. A radar line is a slice, not a full map. A satellite elevation change is a symptom, not a direct view. We are learning to read Greenland the way a doctor reads a pulse and a shadow on an X-ray, recognizing patterns, predicting risk, but rarely opening the body to see the mechanism directly. And the mechanism is alien in its own quiet way. Channels can close as quickly as they open, pinched shut by the slow creep of ice. A lake may drain, then the corridor collapses, and the system resets as if nothing happened, except for the scar on the surface. A shallow depression that gradually fills with snowfall, a faint crease of new crevasses that lingers like handwriting. Sometimes the only lasting evidence is a change in how a glacier moves, a subtle acceleration or slowdown that becomes visible on velocity maps and GPS records long after the lake itself has gone quiet again. At the edges of the science, there are more speculative ideas, not claims of monsters or machines, but suggestions that the ice sheet might behave more like a networked system than a set of independent parts. In Antarctica, some subglacial lakes are known to fill and drain in linked cascades, passing water along in sequences that look almost coordinated. Could Greenland too contain chains, reservoirs connected by pathways that are mostly closed, mostly dormant, but capable of waking? If one basin drains, does it lower pressure somewhere else and invite another to fill? Does a cascade move under the ice, one reservoir handing water to the next, leaving only subtle rises and falls at the surface like signals in a language we barely understand? If that's true, then a vanishing lake is not an isolated event. It is a shift in a broader circulation, an under-ice weather system made of liquid rather than air. And like weather, it may contain tipping points, conditions where the drainage network reorganizes abruptly, altering friction and flow across regions far larger than the lake itself. The unsettling part is what this implies for the future. Greenland is warming. Surface melt is increasing in extent and duration. Each summer, more water is produced at the top and forced downward through cracks and moulins. The intuitive story says, more meltwater means more lubrication, faster flow, more ice delivered to the sea. But reality is more paradoxical. Sometimes increased meltwater carves efficient subglacial channels that lower basal pressure and can slow parts of a glacier, stabilizing them, at least temporarily, by giving the water a fast escape route rather than letting it spread and lift the ice. Which means that somewhere under Greenland's bright emptiness, there may be lakes that have existed for decades, quietly filling, quietly held by ice and sediment. And there may be others that have only recently formed, born from a warming surface and a shifting bed. Some will drain harmlessly, their water dispersing into channels that reach the coast as cloudy plumes. Others may trigger fractures, accelerations, and the kind of subtle reconfiguration that only becomes obvious years later, when a familiar glacier front begins to behave differently, calving with a new rhythm, or sliding with a new steadiness that models struggle to explain. And because all of this happens out of sight, we are left with a peculiar kind of suspense, the sense that the ice sheet is keeping ledges we can't read. A record of pressure, volume, pathways opening and closing like doors in a corridor. In the Beaufort Gyre, the stored water is a dome under a lid. In Greenland, the stored water is a heartbeat under a body, sometimes slow, sometimes sudden, sometimes pausing long enough to make you wonder if it ever existed at all. One day, a satellite will trace a familiar section of the ice sheet and notice that a surface depression has deepened again. Subtle at first, then undeniable. A lake has drained, or a lake has filled. The signal will pass through servers, through models, through quiet conversations late at night. And in the time it takes for us to name what happened, the channels beneath may already have closed, the water already gone, the system already moved on. Under Greenland's ice, hidden reservoirs appear, then vanish. Not because they are illusions, but because the Arctic has a talent for making its most consequential movements in silence. And as we watch the surface breathe, rise, fall, scar, smooth, we're left with the same question the Beaufort Gyre asked in a different language. How much water can be stored beneath the ice before the Arctic decides to let it go? And how many times can it do so, without leaving a sound we can hear? Story 12. The Northwater Polynya. Under Greenland's ice, hidden reservoirs appear, then vanish. Not because they are illusions, but because the Arctic has a talent for making its most consequential movements in silence. And as we watch the surface breathe, rise, fall, scar, smooth, we're left with the same question the Beaufort Gyre asked in a different language. How much water can be stored beneath the ice before the Arctic decides to let it go? And how many times can it do so without leaving a sound we can hear? If Greenland's subglacial lakes are the Arctic's secret plumbing, then there is another kind of secret, one that doesn't hide under kilometers of ice, but sits in plain sight, daring you to explain it. A wound that refuses to close. A patch of dark water that returns again and again to a place that should be locked shut, sealed, and silent. Between northwest Greenland and Ellesmere Island, in the narrow corridor of the Nares Strait, winter arrives with authority. Temperatures drop, daylight thins, and the sea tries to become a single hard surface, an ice bridge binding two continents. And yet, in that same season, a recurring opening forms, an oasis of exposed ocean surrounded by a world of white. It's called the North Water Polynya. To some scientists, it's a system: winds, currents, ice dynamics, heat exchange. To the Inuit who have lived with it for generations, it is something closer to a reliable miracle, an opening that feeds life when everything else starves. And to early explorers pushing north into the high Arctic, it could look like a promise or a trap, a doorway the Arctic keeps reopening, not for our convenience, but on its own terms. Polynyas are not impossible. They're known features in polar seas, areas where ice fails to form or is swept away. But the North Water has always carried an extra weight, because it's not just open water. Its intensity, its abundance. It's a concentration of birds, seals, whales, and the people who learned to read their movements like scripture. In a region where a single mistake can cost you fingers, eyesight, or life, this opening becomes more than geography. It becomes a calendar, a pantry, a hunting ground, a meeting point between human survival and a living sea. Imagine moving through a winter that doesn't simply get cold, but seems to erase color. The land is bone white, the sea is stone blue under ice, and the sky is a long, dim lid. In that world, the Polynya is a break in the spell, a place where the ocean breathes. Steam can rise from it in certain conditions, a faint ghost mist drifting low over dark water. Even the sound changes. Ice is quiet until it isn't, until it cracks, groans, and shifts like a living roof. Open water, by contrast, has its own voice. A low, wet hush, the slap of tiny waves, the soft knocking of Fraser ice forming and breaking apart like glass beads. The why begins with the shape of the place. The Nares Strait funnels water between the Arctic Ocean and Baffin Bay, a narrow passage that can behave like a gate. In winter, ice can jam and lock, forming bridges and arches that hold back drifting flows. In some years, these ice arches stabilize the strait, limiting the flow of sea ice southward. In other years, the arches fail and ice streams through like traffic released. The North Water sits in this tension zone, where ice wants to press down and close the surface, and the ocean keeps finding ways to resist. Strong winds can push newly formed ice away from the opening as fast as it grows, exposing water to the sky, forcing the sea to keep losing heat, to keep trying again, to keep failing. Currents can bring in slightly warmer water from the south, not warm in any human sense, but warm enough to matter at the freezing point, warm enough to eat the underside of thin ice, warm enough to prevent a perfect seal. Tides knead the ice edge, flexing it, fracturing it, feeding small cracks that become lanes, then leads, then a broad, stubborn dark patch that refuses to freeze over completely. But even when you can trace the mechanics, a feeling remains: persistence. The North Water doesn't behave like a random accident. It behaves like a recurring feature, a reopening. Year after year, it returns as if the Arctic has decided there will always be one place where the ocean shows its face. That recurrence shapes life in ways that border on the unbelievable. In the cold months, when most of the surrounding sea is capped and light is scarce, the Polynya becomes a biological engine. Open water allows oxygen exchange. It allows light to touch the surface earlier and longer. It supports plankton blooms that can ignite the entire food chain from the bottom up. Small organisms feed fish. Fish draw seals. Seals draw polar bears. And above them, seabirds gather in numbers that make the sky look textured, moving, alive. In a world that looks empty from far away, this one opening becomes crowded with breath and motion. For Inuit communities in the region, particularly in northwest Greenland and the Canadian High Arctic, this isn't an abstract ecological story. It is lived knowledge, inherited knowledge. The Polynya has a name in Inuktitut, Pikiala Sorsuak, often translated as the Great Upwelling or the Great Polynya, a description that carries both respect and precision. Hunters learned the timing of migration, the behavior of ice, the safe routes, and the dangerous ones. Where thin ice hides beneath snow, where pressure ridges can break a path, where currents make the surface unreliable. They learned how to travel with the wind's mood, how to read a distant haze over open water, how to recognize the difference between ice that will hold and ice that only looks like it will. There is a different kind of map that forms in a place like this. Not lines and coordinates, but memory. A memory of where the sea stays open, where narwhal and beluga might surface, where seals keep breathing holes, where the first birds return, where a traveler can find food in a landscape built to deny it. And that human relationship with the North Water runs deep in time. Long before the world's navies and surveyors arrived with compasses and logbooks, people were using this opening as a hinge between seasons. It wasn't permanent in the sense of a fixed lake, but reliable enough to build life around. Reliable enough that the opening itself becomes part of culture, part of story, part of survival strategy. Then the explorers arrived, and the Polynya became a stage for a different kind of drama. In the 19th century, as expeditions aimed for the high latitudes with the obsession of an era convinced that blank spaces were insults, the waters between Greenland and Ellesmere Island were both a corridor and a barrier. Ships pushed north through Baffin Bay, seeking a way through or around the ice. They learned quickly that the Arctic does not reward confidence. It rewards patience, humility, and luck, often in that order. To an expedition starving for progress, open water could look like an invitation. The idea was seductive. If there is open sea here, perhaps there is open sea farther north. Perhaps the ice is breaking. Perhaps there is a route. And sometimes the North Water did provide breathing space, a place to hunt, to restock, to survive the season. The same abundance that sustained Inuit hunters could sustain desperate crews. Seals, birds, occasional whales, life gathered here, and where there is life, there is a chance to keep going. But the Polynya could also be cruel in its hopefulness. Open water surrounded by ice is not the same as a clear passage. It can be a pocket, a basin, a window that closes behind you. Wind can shift in hours. Ice can compact overnight. A ship can move into open water, feel the relief of motion, and then find itself hemmed in by new pressure as the flows tighten like jaws. In journals and reports, you can sense how the Arctic rearranged itself around human intention. Men wrote about leads opening as if providential, and then described days later a world that locked up so hard it felt like punishment. The same stretch of sea could be a corridor one week and a prison the next. The North Water, sitting at the edge of this volatility, seemed to mock any belief that the Arctic could be mastered simply by desire. And yet, it kept reopening. That's where the gateway feeling begins to creep in. Not as supernatural proof, but as an emotional truth. Because the North Water is not just open water. It is a repeated exception. It is a place where the Arctic's rules soften, briefly, and then harden again. A place where the ocean becomes visible in the heart of winter darkness, where life gathers, where humans have historically been drawn, because they had to be. When you listen to modern scientific explanations, you can feel the confidence of systems thinking. But stand at the edge of the Polynya in your mind. Dark water, steam, birds wheeling, ice ridges stacked like ruined walls. And another kind of logic appears. The logic of thresholds. Why here again? Why does the opening form with such stubborn regularity in this particular geometry, in this particular corridor? Why does it so often bloom into an ecosystem that seems almost too rich for its latitude? And why does it carry such historical gravity, appearing again and again in survival stories, hunting routes, expedition plans, and near disasters? Some researchers point to heat brought upward from deeper layers, a subtle, persistent delivery of energy. Others emphasize the ice factory effect, new ice forming, being pushed away, forming again, a relentless cycle that keeps water exposed. Still others highlight the role of ice arches. When they form, they stabilize conditions that can help maintain the Polynya. When they fail, the entire balance shifts, and the opening can shrink, relocate, or behave unpredictably. And in the last decades, another layer has entered the story: change. The Arctic is warming faster than much of the planet. The ice is thinning, the seasons are bending. That means the North Water, once permanent by pattern, may be becoming something else. If the ice arches form less often, if wind regimes shift, if currents change, the Polynya could expand, weaken, or relocate. The gateway might widen, or it might flicker. For Inuit communities, that instability isn't theoretical. A Polynya that shifts behavior changes hunting, travel, safety. Thin ice patterns can become more deceptive. The timing of animals can drift. What was once a dependable rhythm becomes a set of guesses with higher stakes. The very thing that once made survival possible, a reliable opening, can become more hazardous if it stops behaving like itself. And that leads to a darker question. What if the North Water has always been a kind of contract, one kept by the Arctic's old mechanics? Wind, current, arch, ice. If those mechanics change, what happens to the contract? The mystery then isn't that science has no answers. It's that the answers describe a living balance, and living balances can tip. The North Water feels like a doorway because it is a boundary between states, frozen and unfrozen, starvation and abundance, isolation and passage, certainty and risk. It is the Arctic showing you briefly that it can be different, while also reminding you that it controls the timing. And just like Greenland's subglacial lakes, it teaches the same lesson in a different form. Water moves where you cannot see it. Heat rises in subtle ways. Forces you barely notice, wind direction, current speed, the shape of a coastline, can decide whether a sea becomes solid or stays open. The Arctic doesn't need drama to be powerful. It doesn't need a roar. It can open a patch of ocean in the dead of winter, feed an entire living web, guide human footsteps and sled runners and ship captains toward it. And then, when the season turns, allow it to close again as if nothing happened. So when we talk about the North Water Polynya as a permanent opening that shouldn't stay open, we're really talking about a recurring permission, a repeated exception that has shaped survival and history in the far north. And the haunting thought is this: if the Arctic has always kept one door cracked open in the Nares Strait, an opening that drew life, drew people, drew stories, then what does it mean that the door's hinges are changing? Because somewhere between Greenland and Ellesmere Island, in a place where maps go quiet and the horizon feels unfinished, the North Water will open again. The question is whether it will open the way it used to, or whether, in a warming century, the Arctic is preparing to rewrite even its oldest exceptions and leave us standing at the edge of dark water, listening for a pattern that no longer answers back. Story 13. The Lost Aircraft. Under Greenland and Arctic Ice. Maybe that's the most unsettling part of the North Water, how it teaches us to distrust the word permanent. A door that opens where ice should seal, a breathing space that returns again and again, like the Arctic refusing to be entirely closed. But if one kind of mystery is an opening, the next is about swallowing, because not far from that dark water, across Greenland's pale spine, across the places where wind sharpens the horizon into a blade, there is another kind of exception the Arctic keeps rewriting. Not an opening in the ice, but an erasure beneath it. A slow, methodical disappearance where the evidence doesn't rot, doesn't scatter, doesn't sink into a warm sea. It simply descends. Under Greenland and the high Arctic, the landscape isn't only frozen, it's layered. Snow falls, then hardens, then gets buried by the next storm. Years compress into decades, decades into centuries. And in that steady pressure, the ice becomes a moving archive, one that does not preserve the way a museum preserves, with labels and glass cases and neat explanations. It preserves like a secret. Because in the Arctic, crashes don't always look like crashes for long. A damaged aircraft might lie in clean white silence by morning, half buried by drift. Within weeks, the shape softens. Within a season, it becomes a faint hump in the snowfield. And then, slowly, inevitably, the ice sheet does what it was born to do. It takes weight into its body and it starts to carry it. This is the strange physics of loss up here. On a map, a plane goes down at a point. Latitude, longitude, a final coordinate. But on the ice, a point is never a point for long. Snow accumulates. Ice flows. The whole surface creeps, centimetre by centimetre, year by year, like a continent learning to walk. And the wreckage, locked inside, becomes a passenger. A moving crime scene with no fixed address. The idea feels almost poetic until you picture what it means in practical terms. Searchers arrive with the last known position. They look for debris. They scan for metal. They circle and recircle, expecting the world to behave the way it behaves in warmer places, where time leaves a signature: rust, rot, scattering, collapse. But the Arctic doesn't sign its work. It just quiets it. During World War II, Greenland became something it had never been in human memory: a corridor, a stepping stone across the North Atlantic, a place where airfields and weather stations were scratched into ice and rock because the war demanded routes that didn't exist before. Aircraft began to pass over the interior, over fjords, over featureless white, where there were no towns, no roads, no eyes, only weather. And Arctic weather is not simply bad. It is intelligent in the way a maze is intelligent. It doesn't just oppose you, it reorders you. Visibility collapses into milk glass. Winds push planes off course without a sound. Instruments drift. Radio becomes fragile. A horizon disappears, and suddenly you're flying inside a blank page. Many of the losses began like that. Routine on paper, uncertain in the air. A ferry flight, a supply run, a training mission. A formation crossing that should have been straightforward if the sky remained honest. But Greenland's interior is a place where honesty is not guaranteed. One of the most famous cases, and one that has become almost mythic in Arctic aviation history, began in 1942 with a group of US Army Air Force's planes ferrying across the Atlantic. A storm moved in, fast, dense, and merciless. And in that storm, several aircraft were forced down onto the Greenland ice cap. Pilots managed controlled landings, bellies skimming snow instead of sea, because sometimes the ice is the kinder option. And for a moment, it must have felt like survival. Men climbed out into wind that could carve skin. They gathered what they could. They watched their aircraft settle into the whiteness like tired animals. They waited in a world with no landmarks, no shelter, and no certainty that anyone would find them before the cold did what cold always tries to do. Remarkably, in that incident, the crews were rescued, an achievement in itself, given the era and the conditions. But the planes were left behind, too heavy to recover, too expensive to justify. The war moved on, and Greenland did what Greenland does. It covered the evidence. Years later, decades later, those aircraft were no longer on the ice. They were in it. This is where the story turns from military history into something eerier, because what is lost under an ice sheet does not simply vanish. It goes into storage. Layer by layer, the snow compacts into firn. Firn turns to glacial ice, and the object becomes entombed in a material that is both solid and slowly flowing. The plane is not only buried, it is being carried through time. In the late 20th century, when technology caught up with old rumors, searchers went back for some of these wrecks. Not because they expected survivors, there could be none, but because the Arctic has a way of making the past feel reachable. If the wreck is preserved, maybe the story is preserved. Maybe the aircraft is still there, still intact, still waiting like an unopened letter. And in at least one celebrated recovery, that belief proved almost disturbingly true. Beneath dozens of meters of ice, an aircraft was found that looked less like a relic and more like a time capsule. Metal skin, serial numbers, internal components, all sealed away from weather, sunlight, and most forms of decay. The excavation was part engineering, part archaeology, part obsession. Hot water drills and shafts cut into the ice like surgical incisions. Sensors listened for the faint metallic echo of a hidden body. And when they finally reached it, they didn't dig it out so much as unearth it from a substance that didn't want to let go. Imagine the first glimpse. A curve of aluminum emerging in blue shadow, beaded with meltwater. The shape of a wing or fuselage rising from darkness like something waking. It's tempting to treat that as a triumphant ending. Proof that nothing is truly lost, only delayed. But in the Arctic, recovery often deepens the mystery instead of solving it. Because the moment you accept that a plane can sink into an ice sheet like a coin into wax, you start to realize what else might be down there. How many other crashes were never marked by rescue? How many last radio calls were swallowed by static, never triangulated, never followed by a flare, never followed by a trail? And what happens to those wrecks over time isn't simple burial. The ice is not a static tomb. It deforms. It flows downhill, imperceptibly but relentlessly toward the coast. It can crack, shear, fold. A plane might remain intact for decades, then be twisted by slow pressure like a hand tightening around it. Fuel can leak and freeze and seep into layers. Ammunition and cargo can migrate as the structure collapses. The wreck becomes a strange, evolving fossil, part machine, part geology. In some cases, the ice doesn't keep its prize forever. Glaciers move, they carve, they melt at edges, and occasionally, a piece of the past reappears far from where it entered. Metal fragments emerging from dirty ice near a glacier's snout. A hint of paint, a torn strip of fabric, a cereal plate blinking in sunlight like an eye opening after a long sleep. When that happens, it feels less like discovery and more like the Arctic returning evidence on its own schedule. There are stories from Greenland and other polar regions of hunters or researchers stumbling across wreckage that shouldn't be there. An engine half exposed, a section of wing, a scatter of parts that look fresh, until you read the manufacturing marks and realize you're staring at another decade's definition of modern. The plane didn't move on its own, of course. The glacier carried it like a conveyor belt, then quietly delivered it where melt finally loosened the grip. And the unsettling implication is that the Arctic can both hide and reveal with the same mechanism. It doesn't need intention, it only needs time. But not all aircraft losses are as documented as wartime incidents with recorded routes and known crews. Some are quieter and therefore more haunting. A flight that vanished in poor weather. A patrol that never returned. A transport plane that went missing over a featureless expanse where search aircraft could fly for hours and see nothing but snow and cloud, and the occasional illusion of shadow. In those cases, the mystery becomes layered in a different way. It isn't only, where did it go down? It's, what does down even mean here? Because an aircraft can crash and leave almost no visible trace after a single storm. Its debris can be scattered and immediately buried. Its final position can be wrong by dozens of miles, because the crew was fighting wind drift and instrument error. Even if the wreck is near where you look, the surface you search is not the surface it fell onto. Years of accumulation can raise the ice, smooth it, erase the contours. A crevasse can open and swallow sections whole. An impact crater can be filled and flattened until it becomes a rumor. And that means search and recovery in the Arctic isn't like searching a forest or a mountain. It's closer to reading a book whose pages are moving while you read them. Paragraphs sliding under the binding, lines reordering themselves. Investigators become detectives of physics. They study wind patterns on the day of disappearance. They reanalyze radio logs. They calculate drift, not of a floating raft, but of a glacial surface over decades. They use radar that can see into ice, but only if the layers cooperate. Only if meltwater hasn't created reflective noise. Only if the bed topography doesn't distort the signal. They interpret anomalies, a bright spot, a shadowed void, a line that could be a crevasse or could be metal. And even when they find something, the Arctic rarely offers a clean narrative. A wreck might be intact enough to read its serial numbers, but not intact enough to explain the final moments. A flight might have been forced down by weather, but why was it there at all? Was it off course? Did it attempt a shortcut? Did instruments fail? Was there sabotage, human error, simple misfortune? In warmer oceans, a missing aircraft becomes a race against time because salt and pressure destroy the evidence. In ice, time does not destroy in the same way. Instead, time relocates. It hides, compresses, transports, and sometimes preserves so well that the past feels present again. Too present, like an old voice suddenly speaking in a quiet room. There's a particular kind of eeriness to machines preserved in ice because machines are supposed to belong to progress. They are symbols of forward motion. Seeing them trapped in a frozen archive reverses that meaning. It suggests that in the Arctic, the future can be paused, stored, and forgotten as easily as the past. And Greenland's ice sheet, immense and heavy and alive with slow movement, becomes more than a backdrop. It becomes an actor, a force that participates without intention, a custodian that keeps what falls into its care, whether it was meant to be kept or not. This is why the phrase "lost aircraft under Greenland" carries such a strange charge. It isn't only about tragedy or war or misadventure. It's about the idea that the Earth can take an object from our era and file it away inside a moving layer of time. A plane disappears from the sky, and the world continues. The war ends. The crews go home. Families age. Runways change names. Engines evolve. Satellites begin to watch the planet from above. And all the while, beneath Greenland's bright surface, the wreck continues its slow migration, locked in darkness, traveling inch by inch in a direction no pilot ever chose. So when people return, when they drill down and listen and cut into the ice, the feeling isn't only curiosity, it's confrontation. Because you're not just finding a plane, you're finding a moment that never got to finish. And in a warming century, that confrontation becomes even stranger. As temperatures shift, as melt patterns change, as glaciers thin and retreat, the Arctic begins to loosen its grip on what it has held. Wreckage that once would have remained buried for centuries may reappear sooner. Not as a neat artifact, but as fragments pushed out by meltwater and gravity, arriving in the open world without context, evidence released without explanation. Which raises a quiet, unsettling question. How many mysteries are still sealed simply because the ice has been stable enough to keep them sealed? And what happens when that stability changes? Somewhere under Greenland, there are aircraft that have not been named in documentaries, that have no famous recovery story attached, that exist only as missing entries in old logs and family memories, and a last known position marked with a pencil circle. Somewhere, there may be cabins of frozen instruments, cargo still strapped down, radios still tuned to a frequency that once carried a human voice. Somewhere, there may be wrecks broken by pressure into unrecognizable shapes, metal folded and pressed into the ice like a signature. And perhaps the most haunting part is that the Arctic doesn't treat these as separate stories. It treats them as material, as weight, as something to be absorbed and carried. A door in the Nares Strait opens and closes, as if the ocean itself is breathing. And over Greenland, the ice does something similar in its own way, taking in what falls from the sky, then slowly, silently, moving it through the planet like a secret passed hand to hand. We imagine disappearance as an ending, but under Arctic ice, disappearance can be a process that never really stops. Because the wreck is still there. It's just not where it was, and it's not finished becoming whatever the ice intends it to be. So the next time you look at Greenland on a map, so clean, so white, so seemingly empty, remember that it is not emptiness. It is storage. It is motion disguised as stillness. It is a place where aircraft can fall and decades later be found again. Not as wreckage, but as a message from a past that never fully sank. And if the Arctic is changing, if the hinges of its oldest patterns are shifting, then we may be entering an era where the ice begins to return what it has held. Not with answers, just with proof. A piece of aluminum in the melt, a number stamped into metal, a ghost in the white, rising quietly toward the surface as if the ice sheet is finally ready to speak, without telling us what it means. Story 14. The Arctic shelf methane. Pingo-like features. So the ice begins to return what it has held. Not with answers, just with proof. And that idea of the Arctic as a vault that moves doesn't end with metal and serial numbers buried in Greenland's white. Because beneath the clean map of the North, beneath the flat, pale skin of the shelf seas, there is another kind of storage at work. Not aluminum, not rivets, not the fossilized geometry of wings, but something older, quieter, and far more volatile. Carbon locked away when the world was colder, when coastlines were different, and when the Arctic was not an ocean you could sail, but a frozen plain stitched to the continent. When we imagine the Arctic, we tend to picture one surface: ice, snow, sky. But the Arctic has layers, and some of its most unsettling mysteries are not trapped in the ice sheet above, but sealed in the sediments below, pressed under water and mud, held in place by cold, pressure, and time. A cold chemistry, a slow bargain. Out on the shallow continental shelves, the broad underwater margins that ring Siberia, Alaska, Canada, researchers have found strange dome-like forms, circular ridges, subtle mounds that rise from the seabed like blisters on a sleeping animal. In sonar and bathymetry, they look almost deliberate, rounded, swollen. Features that resemble pingos, those ice-cored hills that rise on Arctic tundra when groundwater freezes and pushes upward, lifting the earth like a slow breath. On land, pingos feel almost friendly. They are part of the Arctic's surface language, hills that grow in silence. But at sea, these pingo-like features belong to a different grammar. They sit in the dark, under cold water, in regions where subsea permafrost, frozen ground left over from the last ice age, still persists like a ghost coastline. Back then, sea level was lower. Vast areas of what is now seabed were dry land, exposed to brutal air temperatures, then drowned, but not immediately thawed. Subsea permafrost can linger for thousands of years, insulated by sediments and by the Arctic's own chill. And within or beneath that permafrost, methane can accumulate, produced by microbes eating ancient organic matter or migrating upward from deeper geological reservoirs. Methane is invisible. It is buoyant. It seeks escape. But in the right conditions, cold enough, pressurized enough, it can be stored in strange forms, trapped as free gas in pockets, or locked into methane hydrates, ice-like crystals that cage the gas inside a frozen lattice. It's the kind of substance that behaves like a riddle, ice that isn't quite ice, and fire that can live inside cold. The domes on the Arctic shelf have become, in some circles, an uneasy symbol of this buried chemistry. Are they benign? Slow-formed mounds shaped by frozen processes, stable features that simply record the Arctic's past? Or are they pressure cookers, structures where gas gathers beneath a cap, waiting for a trigger? And if a trigger comes, what does release look like here? A gentle seep? A persistent leak? Or a sudden blowout? An eruption from the seabed that leaves a crater behind like a missing tooth? Researchers working in Arctic shelf seas have reported active methane seepage in some regions, with plumes of bubbles rising through the water column like underwater storms. In acoustic imagery, these bubble curtains appear as bright vertical streaks, ghostly, almost beautiful, like pillars of static. Sometimes they cluster. Sometimes they align along fractures. Sometimes they appear near mounded features, as if the domes are not just shapes, but symptoms. And it raises a question that sounds simple until you sit with it. What keeps methane down there? And what makes it rise? One proposed pathway begins with the thawing of subsea permafrost. If that frozen layer acts like a lid, an impermeable seal, then warming ocean temperatures, shifting currents, and changes in sea ice could gradually weaken it. Not everywhere at once, but in patches, along old river channels, near faults, where salt water infiltrates, where heat creeps in. A permafrost cap that becomes porous is no longer a cap. Gas that once pooled beneath can begin to migrate upward through newly opened pores and cracks. Another pathway involves hydrates. Hydrates are stable only within a narrow envelope of pressure and temperature. Change that envelope and the cages can dissociate, releasing methane and water, turning a solid into gas. On shallow shelves, the stability zone can be thin and sensitive, its boundaries shifting with relatively small changes in heat or pressure. And the boundary matters because it is not a wall. It is a moving line where locked becomes mobile. Then there is the structural side. The shelf is not inert. It is cut by faults. It responds to seismic shaking, to the slow rebound of land after ice sheets melt, to subtle stresses that open and close pathways over time. Even small disturbances can rearrange sediments, disturb hydrate layers, or connect a gas pocket to a new escape route. This is where the debate starts to feel like a detective story. Because the domes themselves, these pingo-like features, can be read in more than one way. Some researchers argue for gradual formation. Ice-cored mounds built by freezing and pressurizing water within subsea sediments, similar in concept to terrestrial pingos. In that view, methane seeps might be adjacent, part of a broader seep field, not necessarily the dome's internal engine. Others suggest a more gas-driven model. Methane migrating upward deforms sediments, inflating layers from below, especially if the gas is trapped beneath a stronger stratum. A slow blister, lifted millimeter by millimeter. The seabed rises almost imperceptibly while pressure builds beneath. And then, in the most unnerving scenario, the dome is not a stable hill at all, but a prelude, a pressure bulge before failure, a place where gas and sediment are in a tense stalemate, with the seafloor held up by the very force that threatens to tear it open. In parts of the Arctic, scientists have documented craters, large depressions on the seabed that look like something once pushed up and then collapsed. In some cases, the surrounding rims suggest a powerful release, an expulsive event strong enough to excavate sediments. The details vary, and the exact causes are still debated. But the pattern, mounds, vents, craters, invites a certain kind of dread. It looks like the seafloor has a memory of rupture. And it forces another uncomfortable question. If blowouts happen, how often do they happen without witnesses? The Arctic shelf is vast, seasonally inaccessible, sparsely instrumented. A sudden methane eruption on a stormy night under thin ice could leave little immediate trace to human eyes. The bubbles might rise, dissolve, spread, be carried by currents. The seabed might collapse into a crater, then soften under slow sedimentation. Unless a survey passes over the right place at the right time, the event becomes one more silent incident in a landscape that does not keep diaries. Still, methane leaves hints. It changes chemistry. It feeds certain microbes. It can create carbonate crusts on the seabed, hard mineral deposits formed when methane oxidation alters the local environment. It can attract ecosystems, clams, worms, bacterial mats, pale gardens nourished not by sunlight, but by seepage. Under a remotely operated vehicle's lights, these seep communities can look like something from another planet. Life clustered around an invisible breath. And yet, the climate angle hangs over it like low cloud. Methane is a potent greenhouse gas. If large amounts reach the atmosphere, it can amplify warming on relatively short timescales. The question is not merely whether methane exists under the shelf, it does, but how much can escape, how quickly, and in what form. Many plumes dissolve before reaching the surface, especially in deeper water, where methane can be consumed by microbes or transported laterally. On very shallow shelves, however, the pathway is shorter. The distance between seabed and sky is reduced, and the line between a local seep and a global consequence feels uncomfortably thin. Mainstream science stays careful here. It emphasizes uncertainty, complexity, the need for more measurements. It notes that methane dynamics depend on local geology, sediment type, ocean mixing, and biological consumption. It warns against assuming every mound is a ticking bomb, or that every seep is accelerating into catastrophe. But careful does not mean comfortable, because uncertainty cuts both ways. It means we cannot confidently predict a blowout, and it also means we cannot confidently rule out rare, high-impact releases. The Arctic is the kind of system where slow change can cross thresholds, and thresholds, by definition, are not announced. They are discovered only after you step over them. There is also the human layer, the quiet proximity of industry and infrastructure. Shipping routes lengthen. Offshore projects expand and retract with politics and price. Cables, pipelines, platforms, research stations. Artifacts of modern intent placed atop an environment that is, in its own way, alive. A seabed that can swell and vent is not just a scientific curiosity. It is a foundation that may not always behave like a foundation. And this is where the metaphor returns, uninvited. A plane disappears into the ice, and decades later, it drifts toward the surface because the storage conditions changed. Shelf methane follows the same logic, written in chemistry instead of metal. A stored thing that becomes mobile when the rules shift. The difference is scale and consequence. Imagine a survey ship moving across a grey Arctic sea in late summer. The horizon is low and empty. On board, the instruments translate darkness into maps. A field of rounded mounds appears, dozens, perhaps hundreds, each a quiet rise in the sediment. The ship passes over one, and the acoustic return flashes with a vertical plume, a column of bubbles rising like a silent flare. No sound reaches the deck, no visible sign, unless the sea is still enough to show subtle slicks, small disturbances, a faint shimmering that could be dismissed as light. And yet, under the hull, something is moving upward from a depth that remembers the Ice Age. To chase those hints, teams combine tools that feel almost like forensic work. Multi-beam sonar draws the seafloor in fine relief, revealing domes and rings that the naked ocean would never betray. Sub-bottom profilers and seismic lines peer into the sediment layers, looking for gas-charged zones, frozen horizons, buried channels, places where fluid could focus, or where an old permafrost table still holds. Cores are pulled up like memory samples, cold mud that can release tiny streams of gas when pressure changes, layered with the signatures of ancient shorelines, old rivers, eras of freezing and drowning, compression and seepage. And even the map is unstable. The Arctic shelf is scoured by ice keels that gouge the seabed, reshaping sediments, opening microfractures, dragging material into ridges. Storms and shifting currents redistribute fine silt, burying one vent and exposing another. In some places, talics, unfrozen corridors within permafrost, can form beneath old riverbeds or warmer water patches, becoming hidden chimneys that connect depth to surface. A seep field that looks quiet one season can look restless the next, not because the planet suddenly changed its mind, but because the surface layer rearranged the exits. Coordinates are logged. The ship continues. The Arctic remains outwardly serene. So are these pingo-like features slow pressure cookers or future blowouts? Maybe the honest answer is that they are both, depending on the place, the year, the sediment, the crack, the storm, the temperature, the unseen history of a single mound. Maybe some are ancient scars, formed long ago, now quiet. Maybe some are living structures, growing as gas accumulates, deforming the seafloor like a heartbeat you can only detect with instruments. And maybe a few are thresholds waiting to be crossed, systems balanced on the edge of release. The Arctic doesn't always give us events. Sometimes it gives us hints, shapes in sonar, chemistry in water samples, a plume that appears, then fades, then returns somewhere else. Proof without closure. And if the ice sheet was a vault that returned a piece of aluminum like a whisper from the 20th century, then the shelf is a deeper archive, older and less personal, speaking in molecules instead of names. The question is not only what it will return, it's when, and whether we will recognize the message in time, or only later, staring at a new hollow in the map, trying to decide if the Arctic has simply exhaled, or if something underneath has finally decided to break the seal. Story 15. The ice shelves, hidden caverns, and sudden collapses. If the ice sheet was a vault that returned a piece of aluminum like a whisper from the 20th century, then the shelf is a deeper archive, older and less personal, speaking in molecules instead of names. But molecules are patient. They move through pores and fractures. They seep, they gather, they wait. Ice does something different. Ice does not seep. Ice holds. And then, sometimes without warning, it lets go. Because just beyond those slow pressure cookers on the seabed, there is another kind of suspense suspended over the Arctic. Entire continents of floating ice, latched to the land by habit and temperature, carrying their own hidden architecture underneath. Not caves in rock, not tunnels you can walk through, cathedrals made of absence. Vaulted cavities carved by warmth in a world that looks, from above, perfectly sealed. From the air, an ice shelf can seem like certainty, a white plane that refuses to move, a border you can trace cleanly on a map. But beneath it, seawater is always arriving. It comes in heavy and quiet, pushed by tides, guided by the shape of the seafloor, threaded along channels that no human eye can follow for long. And where that water is even slightly warmer than the freezing point, sometimes only a fraction of a degree, it begins to do what warmth always does in the polar world. It eats from below, not like a fire, not with drama, with patience, with geometry. A shelf can be tens, even hundreds of meters thick, and still be hollowed into something delicate. The underside is sculpted into ridges and scallops, like the ceiling of a drowned basilica. Long grooves run with the tide. Domes form where circulation focuses melt into a single spot. Over time, these shapes can connect, pockets becoming corridors, corridors becoming chambers, until the shelf is no longer simply ice, but a roof over moving black water. And that is where the eeriness lives. The Arctic does not only hide things in its ice the way a freezer hides food, it hides processes. It hides structures that have no reason to exist in the human imagination. Because we do not live beneath ceilings of frozen ocean, listening to their slow renovation by a sea that never stops touching them. Scientists sometimes describe these sub-ice shelf cavities in practical terms: basal channels, meltwater pathways, zones of thinning. But the language can't quite hold the feeling of it. A cavity is not merely space. In the polar world, space is an event. Space is weakness. Space is a future collapse already rehearsing itself, and the shelf knows it. Ice is not a single solid thing. It is a crowded history of snowfall, compressed into crystal, riddled with fractures, strained by flow, stitched and restitched by freezing and melting. It carries internal layers like pages. It remembers every winter. It also carries stress like a nerve. The strange part is that a shelf can endure for centuries while changing from within. Its surface looking calm, while its underside becomes elaborate, unstable, and thin in places no satellite can directly see. It can look unchanged right up until the moment it isn't. Because collapse is not always a slow retreat. Sometimes it is a snapped bone. A calving event is the cleanest version of this. A piece breaks away, a new cliff face is exposed, and the ocean takes the severed slab, rolling it slowly into open water. In that moment, the hidden underside becomes briefly visible. Arches, grooves, scalloped hollows, patterns that look less like nature and more like design. A thing that was roof becomes wall, and for a short time, the cathedral reveals its ceiling. But collapse is something darker. Collapse is when the roof fails everywhere at once. It's easy to picture ice breaking as a simple shattering, like a pane of glass. But large shelves don't just crack, they unravel. The surface, often laced with melt ponds in warm seasons, becomes a network of stress concentrators. Water fills fractures, and because water is heavy and relentless, it pries them open deeper and deeper. This is one of the mechanisms researchers point to: hydrofracture, the idea that surface meltwater forces its way down through crevasses like a wedge, turning narrow cracks into full-depth breaks. At the same time, the underside may already be thinned by intruding warm water, especially where currents concentrate, melt into channels. So the shelf is attacked from above and below, not symmetrically, but in a coordinated way. The shelf itself cannot plan to resist. The roof becomes a lattice. The lattice becomes shards. And then, in a span of hours to days, a structure that felt permanent becomes a field of rubble. The Arctic, to us, is often a symbol of slow change, gradual thinning, creeping retreat. But shelves teach a crueler lesson. Systems that appear stable can carry hidden thresholds. They can hold and hold and hold until a particular week, a particular tide, a particular warm pulse of water, a particular summer of melt tips the balance. Then the change happens at the speed of failure. This is why the imagery feels so alien. When a shelf collapses, it can expose shapes that seem like they belong on another planet. Towering vertical faces, blue-lit caverns, freshly broken ice blocks that look like ruins. Even the soundscape changes. Crevasses pop like distant gunshots. Whole sections groan. The ocean fills with the noise of grinding fragments, and beneath it all is a low, continuous thunder as the sea works its way under the newly broken edge. In some cases, there are hints beforehand. Subtle accelerations, widening fractures, surface lakes forming earlier than usual. In other cases, the signals are ambiguous enough that collapse feels like a shock even to those watching closely. That's not because the science is blind. It's because the shelf is a complicated machine built from brittle material, powered by stresses that shift with weather, tides, and seasons, and then quietly rewritten by warming water beneath. And beneath that, there is another discomforting possibility, that some collapses reveal not only failure, but hidden space. Cavities so large and so shaped that they resemble deliberate architecture, as if the ocean had been carving with an artist's hand. There are places where under-ice exploration has shown enormous vaulted voids, spaces big enough for ships, if ships could survive there. These cavities can form where warm water intrudes and circulates, melting upward into the ice. The flow is guided by the slope of the ice base and the pressure field under the shelf, which means melt is not evenly distributed. It is focused, it is channeled, it is organized. The result can be a roof patterned by long basal channels, like ribs, running tens of kilometers, thinning the shelf along lines that become structural fault zones. When a calving front intersects those channels, the break can follow them like a seam. When surface meltwater arrives, it finds crevasses already stressed by that thinning. The shelf, in a sense, is pre-cut, and so collapse can look sudden, but it is built slowly in the dark. This is the part that ties back to our previous mystery, the quiet methane systems on the shelf seabed. Both stories are about pressure and release, about a world that stores energy invisibly. Methane gathers in sediments under changing conditions, waiting for a trigger. Ice stores stress in layered crystal, waiting for a different kind of trigger. One speaks in molecules, the other speaks in architecture. And yet both are governed by thresholds we don't always see coming. Mainstream science leans on a few key drivers: warming air temperatures that increase surface melt, warming ocean waters that increase basal melting, changes in currents that deliver heat under the shelf, shifts in winds and sea ice cover that allow more open water, more wave action, and more heat exchange at the front. None of these drivers are mystical. They are measurable, physical, increasingly monitored. But the unexplained part is not whether these forces exist. It's how they synchronize. Why a shelf can endure years of stress and then fail in a short window. Why one region collapses while another holds. Why some fractures propagate like lightning while others stall. Why an ocean heat pulse in one season finds the shelf vulnerable, while a similar pulse in another season seems to pass without catastrophe. There are also the strange local effects, small geometry turning into big consequence. A grounding line shifts, changing how a shelf is anchored. A pinning point, an underwater rise that braces the ice, loses contact as the shelf thins, and suddenly the whole system is freer to flex. Flexing increases fractures. Fractures admit water. Water deepens fractures. A feedback loop, once started, can run faster than anyone wants. Then come the fringe ideas, not always embraced, but persistently whispered in the background, that there may be sub-ice circulation patterns we still don't map well enough, warm intrusions that appear and disappear like moods, that there are under-ice caverns and channels so large they behave like resonant chambers for tides, amplifying stress in ways our models simplify, that sudden collapses may sometimes be triggered by distant storms sending long-period swells into regions that used to be protected by sea ice, waves that flex the shelf until the cracks finally connect. Some even speculate about hidden geothermal influence in certain polar regions, local heat anomalies on the seafloor that could warm water from below, subtly reshaping under-ice circulation. This doesn't require volcanoes erupting under the shelf. It only requires the Arctic and Antarctic, both tectonically complex in places, to have small, persistent sources of heat that, over long time scales, matter. But even without the fringe, the feeling remains the same. We are dealing with a landscape that can change overnight, not because it is capricious, but because it is storing its instability until it can no longer do so. And when a shelf collapses, it doesn't only remove a piece of ice. It changes the meaning of the map. Where there was a continuous roof, there is now open water. Where a shelf buttressed glaciers feeding into it, acting like a doorstop against the land ice behind, there may now be less resistance, more acceleration, more flow toward the sea. The collapse is not an ending. It is an opening that the ocean rushes into. In the immediate aftermath, the new edge can reveal an underworld that feels impossible. Freshly exposed blue walls, caves that were hidden as ceilings hours before, water swirling with ice debris like shattered marble. Researchers can photograph the sculpted underside of a carved iceberg and see melt patterns that tell a story. Where warm water flowed, where turbulence focused, where the roof thinned into a weak line. These are forensic scenes, and like all forensic scenes, they suggest a timeline, a cause, a chain of events. But the chain is never fully visible, because the most important actions happened while the shelf still looked whole from above, while the vault was still sealed, while the cathedral still stood. In the Arctic, we are used to mysteries that feel like missing objects, lost ships, vanished aircraft, artifacts recovered from ice. But the shelves offer a different kind of mystery. Not an object missing, but a structure disappearing. A whole platform of ice, gone. And what makes it haunting is that the disappearance is not hidden. It is revealed. It is a scar you can see from space, a coastline that redraws itself, a blank where there was once a continuous field. The Arctic does not always erase evidence. Sometimes it removes the roof and forces us to look down. So the question becomes, what else is being carved beneath the shelves right now, out of sight, under a ceiling that still looks calm? What cavities are widening in the dark? What channels are thinning the structure along lines that will someday become fractures? What warm pulses are arriving under the ice like quiet visitors, shaping the underside into something more delicate, more dramatic, more doomed? And if collapse can happen like a snapped bone, fast, decisive, irreversible, then the most unsettling thought is not that we will witness it. It's that we will get used to it. That the sound of a shelf failing will become background noise in our century. That new hollows in the map will feel routine. That we will watch cathedrals fall and call it seasonal variability, even as the architecture underneath grows stranger, larger, more elaborate, more like a world preparing itself for a different climate entirely. Because the Arctic is not just melting, it is reorganizing. And somewhere under the remaining shelves, water is still moving, still eroding, still building empty spaces with patient precision, vaults within vaults, waiting for the moment the roof decides it can no longer pretend to be solid. The question is not only what the Arctic will return, it's what it will reveal when the ceiling finally drops, and whether, when we stare into that newly opened darkness, we'll recognize it as a natural process we understood all along, or as a message we only learn to read after the cathedral is already gone. Story 16. The pressure ridges and ice quakes. when the ice moves like tectonic plates. The Arctic is not just melting, it is reorganizing. And when a ceiling finally drops, it does not simply reveal darkness below. It changes the way the entire frozen world above can carry weight, tension, and sound. The cathedrals hidden inside ice shelves teach a quiet lesson. Emptiness matters. A hollow space can be the difference between stability and sudden failure. But not all of the Arctic's architecture is carved by warm water in secret caverns. Some of it is built in plain sight, at the surface, by force. And unlike a collapse, which can arrive like a snapped bone, this building is noisy. It announces itself. It warns. It startles. Out on the sea ice, where the horizon is a single pale line and the sky seems to rest on the earth, the Arctic sometimes behaves like stone. It locks. It grinds. It stores pressure the way a fault line does. And when it finally releases, it can sound like artillery. Sharp cracks, rolling booms, and low tremors that make the empty air feel crowded. The sea ice is often imagined as a flat, fragile sheet, something that drifts and fractures like broken glass. But in reality, it is a moving skin under compression. Wind pushes it, currents tug it, coastlines and islands corral it. When two broad fields of ice converge, they don't politely slide past each other. They collide, they heave, they pile up. This is how pressure ridges are born. A pressure ridge can begin with a simple crack, an opening, a lead, a black seam of water that looks like a wound in the white. Then the wind changes, or the current shifts, and the seam becomes a hinge. One plate of ice presses into another, and the flows buckle. Slabs tilt upward like toppled pavement. Blocks shatter and stack. New ice forms in the gaps and freezes the chaos into place. From a distance, a pressure ridge can look like a jagged embankment running for kilometers, an improvised mountain range formed in a single night. Up close, it feels like the aftermath of demolition. Plates of ice the size of cars, tilted at strange angles, jammed together with frozen rubble. Some ridges hide keels below the surface, submerged spines that can extend far deeper than the wall you see, scraping the seafloor in shallow waters and making navigation dangerous for anything that tries to pass. And when a ridge forms, it does not form silently. People who have stood on winter sea ice describe it as a living floor, one that speaks in sudden percussive language. A crack like a rifle shot, a staccato series of pops as a fracture propagates, a long groan rising and falling as if the ice were bending like a gigantic beam. Then the deepest sound of all, the boom. That boom can carry for miles. In open air, low-frequency sound travels far, and in cold conditions it can behave strangely, bending in temperature layers, arriving from directions that feel wrong. A boom heard on a calm, clear night can seem close even when its source is distant. It can arrive without any visible disturbance, leaving the mind to invent one. Modern science offers grounded explanations, but even those explanations keep a faint edge of the uncanny. When stress builds in the ice, the release sends elastic waves through the sheet and into the air. The ice acts as both structure and instrument, converting strain into sound. Certain conditions make it louder. Thick ice, wide unbroken expanses, rapid temperature drops that tighten the surface like a drum skin. Even sunlight can play a role, warming one face of the ice, cooling another, turning small gradients into tension. And yet, the mystery persists in the human layer. Because the Arctic is not a place where you can easily verify your assumptions. You might hear the boom and see nothing. You might feel the tremor under your boots and watch the horizon remain perfectly still. In a landscape with few landmarks and fewer witnesses, sound becomes evidence. And evidence has a habit of becoming story, when the ice moves like tectonic plates. But the Arctic has its own signature events, and one of the strangest is the ice quake. An ice quake is not a metaphor. It is a real seismic event, a fracture or slip in ice that releases energy the way rock does in an earthquake. Some occur in sea ice, as large fields fracture under stress. Others occur in glaciers and ice sheets, when crevasses open, ice falls collapse, or massive blocks carve into the ocean. Seismometers can record them. The signal appears. And for a moment, the ice is no longer background. It is an active, faulted world. This is where the story deepens, because there is a particular kind of ice motion that has captivated researchers for decades. The stick-slip earthquake of an ice stream. An ice stream is a fast-moving corridor within an ice sheet, a river of ice that flows more quickly than the surrounding frozen mass. These streams drain enormous volumes from the interior toward the coast. They are highways of accumulation and loss, and in a warming world, they matter, not as curiosities, but as engines that can accelerate sea level rise. Most people imagine glaciers as slow, inexorable things. They creep, they sag, they grind their way forward in silence. But some ice streams do something that feels almost like a decision. They hesitate, they lock, they store strain at their beds, where ice meets rock, sediment, and water. And then, suddenly, they slip. The slip may be subtle to the eye, maybe centimeters or a meter, but it is huge in terms of mass. Imagine a wide slab of ice, kilometers across, moving abruptly over the land beneath it. The frictional interface releases, and the ice slides as a single body. That movement produces seismic waves that can be detected far away, registering on instruments like an earthquake, but with a different signature, slower and longer, as if the event is stretching time. What governs the lock and what triggers the release? The bed of a glacier is hidden. You cannot watch it directly in most places. You infer it through radar, through seismic reflections, through the chemistry of meltwater that escapes at the margins. And those methods suggest an underworld that is neither purely solid nor purely fluid. Beneath some ice streams lies hard bedrock. Beneath others, a layer of deformable sediment, subglacial till, wet, pressurized, and capable of changing its strength depending on water and stress. If the water pressure rises high enough, it can reduce friction, allowing a slip. If the pressure drops, the ice presses harder onto the bed, locking more tightly. This sounds simple, like a valve, but in practice, it is not. Subglacial hydrology is restless. Channels can open and close. Water can be trapped, then released. Sediment can compact and dilate. The system has memory, and small changes can produce outsized effects. Some stick-slip events appear linked to tides, especially near coasts where the oceans rise and fall can subtly flex the grounding zone, the place where floating ice becomes grounded ice. A tide can change stress just enough to help a locked section release. Other events seem to cluster in seasons, suggesting meltwater input or temperature changes. But not all of them fit neatly. There are slips that occur when surface temperatures are low, when meltwater should be minimal. And there are sequences that stall for weeks, then restart without an obvious surface trigger, as if the bed is responding to a hidden timetable. When the ice moves like tectonic plates, this is what makes the phenomenon feel like a fault line, partial predictability paired with sudden surprise. And because the Arctic is so empty, the sensory experience can be unnerving. The slip may not be heard as an explosion. It might be felt as a slow shudder traveling through the ice, a sensation that the ground is moving without visible cause. In other places, a slip can trigger cracking cascades, sharp reports that bounce across the surface like gunfire, followed by the deeper groan of ice settling back into a new geometry. For researchers camped on the ice, instruments might register the event first. A tremor in the data, a sudden shift in GPS position. Only later do the human senses catch up. The faint vibration in a tent pole, the way a cup of water quivers, the uneasy knowledge that the floor beneath you is not as inert as it looks. There is also a quieter kind of deception in these sounds, the way they can be felt more than heard. Long, low-frequency vibrations, sometimes bordering on infrasound, can pass through the body as pressure, a subtle nausea, a tightening in the chest. On a still day, a person might swear something heavy moved nearby, even when the source was a ridge forming kilometers away. In camps and small settlements, stories circulate of windows rattling on clear nights, of dogs lifting their heads and whining before a distant crack arrives, as if the animals are hearing a faint prelude we can't detect. Researchers studying sea ice have learned that the sheet can behave like a giant resonator. A fracture can launch flexural waves that travel along the ice-water interface, their speed and character shaped by thickness, temperature, and snow cover. The same event can sound different depending on where you stand. A sharp crack near the source, a rolling drumbeat farther away, a single muffled thud beyond that. The ice itself filters the message, the way a cathedral shapes a voice into an echo. And not every ice quake belongs to deep glaciers. In some cold regions, sudden temperature drops can make the ground and near-surface ice contract fast enough to crack. Events sometimes compared to frost quakes. They can happen near lakes, rivers, and even tundra soils with ice-rich layers. A person at home can wake to a boom and think of a collision, a gas explosion, a distant crash, when the real cause was simply the landscape tightening in the cold. All of this complicates the question of interpretation. When an ice stream slips, the seismograph writes a signature, but the signature is not a full sentence. It does not tell you whether the bed was lubricated by a pulse of water, weakened by a change in sediment strength, or nudged by a tide that arrived at the wrong or right minute. When sea ice ridges, the crack is a clue, but it does not reveal which pressure field finally reached its limit. The Arctic gives us signals and withholds the source code. When the ice moves like tectonic plates, the broader mystery is not whether ice can do this, but how the rules might change. The Arctic's reorganization means the boundary conditions are shifting. Warmer air increases surface melt. Warmer water erodes ice shelves and changes grounding zones. Thinner sea ice fractures more easily, altering how pressure ridges form and how stress is distributed across flows. More open water means more wave action, more flexing, more dynamic loading at the edges. In a world like that, the soundscape changes. Booms may become more common in some seasons, less in others. Pressure ridges may grow taller in crowded choke points as ice becomes more mobile, or weaken if the ice becomes too thin to build durable walls. Stick slip events may speed up, slow down, or migrate, depending on how water moves beneath the ice and how the bed responds. And the uncomfortable truth is that we can measure the ice more than we can explain it. We can record seismic events and still debate what they mean for future behavior. We can map the surface in exquisite detail and still not know where the bed will lock next. We can hear the ice's booms, but we cannot always translate them into simple cause and effect. Imagine a winter night on the sea ice. There is no wind. The sky is clear and crowded with stars. The cold feels absolute. The horizon is a perfect ring of white and darkness. And then, without warning, a crack splits the silence. Not loud in the way of a nearby gunshot, but sharp enough to make the body react. Then comes the boom, a low, rolling sound that seems to move through you instead of toward you. You look out across the ice. Nothing changes. No drifting snow, no plume of mist. The world is still. In that moment, what you have is not an answer. You have a signal. The ice has adjusted itself, redistributed stress, corrected its geometry, like a living surface performing maintenance in the dark. And because we cannot always see the mechanism, we fill the gap with story. We imagine battles beyond the horizon. We imagine something beneath us shifting in secret. We imagine the sea ice as a roof and ourselves as listeners inside a vast, frozen cathedral, waiting for the next sound, the next slip, the next sudden reminder that the Arctic is not only a place of melting, it is a place of movement. And somewhere out on the white, tonight, pressure is building again, quietly, invisibly, until the moment the ice decides to speak. The Arctic teaches a different kind of lesson. Out here, nothing truly disappears. It only drifts. It freezes. It sinks beneath a lid of ice and waits. Because the mysteries we've followed tonight weren't carved into stone or written into ruins. They were written into motion, into pressure ridges that crack like thunder, into hidden rivers that rewrite themselves under Greenland, into openings in winter ice that return like a recurring dream. We listened to the sea ice sing. We watched life bloom where light should be too weak to matter. We traced the scars of icebergs that once gouged the seafloor like slow-moving weapons. And we stood at the edge of places we can measure, but still can't truly know. Lakes sealed beneath kilometers of ice, networks that drain and refill in silence, and wrecks preserved so perfectly they feel like time forgot to keep moving. And if there's one thing these under-ice mysteries make clear, it's that the Arctic isn't empty. It's an archive. A cold, shifting vault that preserves evidence, hides cause and effect, and forces us to accept an uncomfortable truth. Even with satellites above and sensors below, the planet still keeps secrets. So if these stories pulled you in, if you felt that strange mix of science and wonder, make sure to subscribe and check out the other documentaries on the channel. Because the unknown isn't rare, it's everywhere. Thanks for watching, and as always, until next time, stay safe.